Hi everyone, welcome to the class. Do let me know everyone if I am clearly visible and audible to all of you or not. Yes, students. Hello, hello, hello. Wait a minute. Yes, students, do let me know. Very good afternoon, everyone. Very good afternoon. So, how are you all? How are you all, everyone? Yes, in the chat box. Hi, Darshan, uh, Shrav, Shrav, I would say. Yes, everyone. Who else? Write something there in the chat box, guys. We are going to we are going to complete the chapter today. So today's class is going to be a little lengthy, right? Maybe 5-6 hours class it is going to be with the breaks, right? Okay, thank you, Kampa. Thank you so much. What about others? Why very few students are ma'am, your voice is repeating, is it? Wait a minute. It's echoing. Why so? Let me just check. Okay. I think now it would be fine. Now tell me. Hi Shelja. Hi Darshan, Shav, Janushika. Very good afternoon. Hi Sandhya. Yes. Now is it fine, guys? Tell me. Now is it fine? Now is it echoing again? Tell me everyone in the chat box and let's start with today's class. So till now guys, what all we have done is we have done atomic number, electronic configuration, we have done enthalpy of atomization, right? The sequence of this we have done ionization enthalpy, we have done metallic radii, we are about to do standard electrode potential today, right, which is a very important topic, right, very important topic, right. So what exactly happens that students get confused in this particular topic, right? So don't worry, I am here, I will not let this topic confuse you. Rest of this table we have done thoroughly, we have done density as well. So in this table you can see everything we have finished except for standard in electrode potential. So let's talk about that. Right everyone, very good afternoon, very good afternoon. So let's talk about standard electrode potential. Guys, your NCERT is in your hands. Tell me. Uh, exactly to which I don't remember, right? Around three questions are, will be there from this chapter. And it's not about this chapter. Sometimes the questions are asked in mix, right? Two concepts from one concept from one chapter, other concept from other chapter are mixed and they make one question. They will ask you the nature of the oxide and they ask you vanadium 3 positive, which is actually green in color, right? What is the nature of this oxide? And they don't tell you that it's vanadium 3 positive. They say there is an oxide of vanadium which is of green color. What is the nature of that oxide? So it's a mixture of 2-3 chapters, right? Yes, today we are going to complete the chapter, right? No matter how much time it is going to take, today we are going to finish this chapter, right? Okay. Yes. So let's see trends in the M2 positive. Just give me a minute. This is causing a little bit problem in writing. Yes, I think this would be better. I'm looking like a gangster otherwise, right? Yes. So everybody, let's see this little bit, winter has started. Okay, so let's see trends in the M2 positive standard electrode potential, right? For that, few things from standard electrode potential that I want to know from you, right? So these things are, tell me, whenever I say here it is M2 positive to M standard electrode potential, tell me whether it's a reduction potential or it's a oxidation potential. If I say M2 positive to M, it means M2 positive is getting converted to M. That means from +2 to 0, the oxidation number is changing. Now, if I say this is the oxidation number change, oxidation number is increasing or decreasing? It is decreasing. So, can we say that this is a case of reduction? This is a case of reduction. That means here they are talking about reduction potential. Okay, that means they are talking about reduction potential. Firstly, this one thing you should be able to understand, that what exactly we are talking about. Are we talking about standard reduction potential? Are we talking about standard oxidation potential? By convention, standard electrode potential is nothing but it is reduction potential only. So that's why it is standard reduction potential. Okay, one thing you should know. Now, these things are a little bit complicated that you will see here. I'll make it easy for you, right? That's why I'm writing something on this left side, right? Because directly though you can also read yourself. Then why you are in this class? Because you want things to be easy for you, right? Now I'll be asking you few questions and I want you guys to answer that in the chat box, right? Okay, yes everybody, tell me. Now if you have M2 positive, that is reduction potential. Now tell me, if I say M2 positive to M, right? Or I would take the reverse of that. Usually reverse is taken. So in the questions you will see that why I'm doing this, right? Let's see, you have M2 positive. Let's see, you have M2 positive, M to M2 positive. There is any metal in the transition series where you are losing 2 electrons and here it is getting converted to M2 positive. That means here oxidation is happening. Now tell me one thing. If this thing is easy, conversion of M to M2 positive is easy, that means this thing is stable and this is unstable, right? This is stable, this is unstable. In that case, reduction potential will be positive, high, or reduction potential will be low, right? You have to tell me about this thing, right? Because usually these kind of questions are related from the value of reduction potential is related to the ease of the reaction, right? So that's why I'm firstly talking about M to M2 positive, which is oxidation. If I say oxidation is easy, that means its reduction is tough. That means reduction is tough, right? Reduction is tough means then M2 positive to M, it will be difficult, it will be tough here. M2 positive to M, this particular reduction is going to be tough. That means its standard reduction potential, E naught reduction potential of M2 positive to M is going to be negative, or you can simply say low, because it does not want to get reduced, right? Okay, because it does not want to get reduced, it is not interested in the reduction, right? So this is a very, very important point here. I want to all of you to write it down in the chat box if that is clear. This is a very, very important point, right? To understand this particular segment, right? That is reduction potential. If I say the reduction potential value is low, that means reduction is difficult. That means oxidation is easy, right? Okay. Now we will do the same thing here, right? We'll do the same thing right here. If you see this here, right? Now we have, if I say M2 M2 positive is difficult, it's tough. If I say M2 positive is tough, in that case, the one that I am talking about is oxidation. That means, am I saying that oxidation is tough means already you are in a maybe stable form and you are getting converted into a unstable form, maybe like this you have, right? If oxidation is tough, then reduction will be easy. Then reduction is easy. That means opposite of this, M2 positive to M, it is quite easy. That means if reduction is easy, that means reduction potential that we say M2 positive to M, that is going to be high. Reduction potential is going to be high. Okay, so these things you just have to understand, that how reduction potential is related to the reaction of oxidation and the reaction of reduction. That's it. Once you know this, things are going to be to remember. Right, everyone? Okay. So now let's do this. Actually, what we should do is, it should be written in little bold. Okay, here we can say reduction is, what we have written here, reduction is easy. That means M2 positive to M is easy. That means reduction potential of M2 positive to M is going to be high. How high and low reduction potentials are connected to the variation of this particular thing, we'll talk about that. Okay, right, everyone? So that is done. Okay, the basic core concept we have done. Now we will understand in the theory part what exactly. Now theory will be more easy for you to understand. Let's see. Now they are saying that in 4.4 table, this is a table that they have, this is a graph that they have given you. They are saying it contains the thermochemical parameters related to the transformation of solid metal to M2 positive. That's why if you remember, I have not just directly said M2 positive to M reduction potential is high, that means reduction will be easy. I have also given you it in the form of oxidation, because we are talking about oxidation here. Though we are talking about the values, the confusing part is we are talking about the values of reduction potential, but we are talking about oxidation. It's like we are talking about this particular reaction, that this is the reaction, but we are talking about the reduction potential. This reaction is oxidation. We are talking about oxidation, but we are talking about the reduction potential of this oxidation. We are saying if this reaction is easy, then its reduction potential, direct relation is, if any oxidation reaction is easy, its reduction potential will be low, right? If any oxidation reaction is tough, its reduction potential is going to be high. Okay, so we are relating these two things here. Now the standard electrode potential, that is the reduction potential. The observed value of E and those calculated using data are compared in this. Unique behavior of, now firstly let's talk about the data. Now here we are talking about the observed values and the calculated values. Observed values are, okay, let's say what we calculate here. We calculate that based on this thing, we calculate. Based on this criteria we have calculated, and observed is experimentally what they have given us, right? So what we have seen, titanium, vanadium, chromium, it is increasing. Then at manganese it will decrease. Okay. Now can you tell me why this decrement is there in case of manganese? Let's study that. Okay, because why we are here to study every single thing that is given in the graphs. So why a dip in manganese? Let's talk about that. So Bacha, we are talking about, this is the first question right, that you should be able to answer in this particular graph, why there is a dip over here, right? Why it is also not increasing. The observed value and calculated value both are same. That means what we calculated, our theory justification, our theory answer is same. Let's see why. We have manganese, 2 manganese 2 positive. If you talk about this particular reaction, this is 4s2 3d5. After losing 2 electrons, it will become 3d5, which is quite a stable configuration. So it is getting converted to a very, very stable configuration, that is half filled. That is why, can I say this reaction will be easy? That means oxidation is easy. But can I say here oxidation is easy? Yes, everybody, tell me. Can I say oxidation is easy? Reduction will be tough. That means E naught reduction potential of this is going to be high. Is going to be low, because reduction is tough. Reduction does not want to take place. So it is going to be low. Or you can just simply remember it from the thing that I have given you here, that if your oxidation is easy, then reduction potential is low. Simple, right? So I have just simply written it here. So just remember, if oxidation is easy, reduction is tough, then reduction potential is low. That's why you will see a dip over here. That's why you have seen a dip over here, right? There is some logic behind that, that why you have seen a dip over here, right? Now, other values. Now understand one thing. We are talking about this sense here. We are saying that if this particular thing is applicable, right, that is our calculated value. From here we are calculating the values. From these calculated values, we can only see a dip in case of manganese, right? Okay. But in case of copper also there should be a dip. Copper it is no. Copper will not see any dip. In case of zinc also we are observing a dip here, right? Zinc is also same. Let me tell you why in zinc also we are observing a dip. In case of zinc also the dip is same. That means that according to that the dip is there even if you have calculated or observed. Let's talk about that. Now let's say why dip in zinc. Why there is a dip in zinc? If you talk about zinc 2 positive, again if you see this is 4s2 3d10. This will be 3d10. That means you are definitely making it easy. You are definitely going into a stable, fully filled configuration. So we can say oxidation is easy. We can say reduction is tough. We can say E naught reduction potential is low here as well. That is why you can see a dip over here. That is why you can see a dip over here, right? That is why you can see a dip over here. So these two things we are able to understand. Why a dip here and why a dip here. Other things you are not able to understand, right? Let me just inform other students as well. Oh, I have not texted the students only. Oops. Okay. Now what I have seen a dip over here, right? These two things are justifiable. That why in case of manganese you can see a dip, why in case of copper you can see a dip, even in calculated values, even in observed value. Why calculated and observed is same here? Because the reasoning of how we are calculating it is correct, right? Now we will see something that is totally opposite. Now can you see in case of three abnormal things you will see here. Okay, that is very important. This one, I'll just mark it. This one, and this one. What are these three abnormal things here? Let's talk about that. If I talk about this one here, observed and calculated is not same, right? Now let me talk about this one, that why observed and calculated is not same. Where should I write it? I'll take an extra page here and I'll just show you with that, right? Why observed and calculated is not same here. So if you talk about cobalt and nickel, right? See, according to calculation only, firstly, we'll talk about why, right? Why observed and calculated is not same? Why observed and now this much detail nobody is going to teach you, trust me on that, right? Why observed and calculated values of which one is not same? Cobalt and nickel is not same. That is a weird thing. Of cobalt and nickel, not same. Let's discuss cobalt and nickel in the same pattern. So firstly, I'll discuss about cobalt. Okay. Firstly, I'll discuss about cobalt. So when I discuss about cobalt here, cobalt is atomic number 27. This is the situation. Now I'll see cobalt 2 positive. Cobalt is nothing but, if I talk about cobalt 2 positive, cobalt 2 positive, cobalt is nothing but cobalt is actually 4s2 3d7, right? This is cobalt, right? 4s2 3d7. Cobalt 2 positive is 3d7. So are you seeing any stable electronic configuration, anything like that, right? Nothing like that you can see. So that's why according to you, there should be a normal increase here, right? A normal increase. Dip is considered. If I say if you see this here, in the calculated values, there is a dip. Dip is only there if I say dip should be there if E0 reduction potential is low. E0 reduction potential is low. Now I am doing the reverse game. Dip means E0 reduction potential is suddenly getting low. If I am saying that E0 reduction potential should be low, that means reduction should be tough. That means oxidation should be easy. Now, can you say anything like oxidation is becoming easy over here? Can you see that oxidation is becoming easy over here? This is any half filled or fully filled electronic configuration. You can't see that. But from electronic configuration, cobalt 2 positive is not easy because it is not getting converted into a stable electronic configuration, right? If I want my dip to be there, that means reduction potential should be, but tell me if this is clear. If I say that E0 value should be low, there should be a dip here, that means reduction potential should be low. That means reduction is not happening easily. Reduction is difficult. That means oxidation will be easy here. But that is not the case, right? Reduction is also reduction here. If you talk about that, ma'am, oxidation is easy. So nowhere I can see that oxidation is easy. Here it is not getting converted into a stable electronic configuration that I confidently say that, oh my god, stable. Like here if you see, we can observe that here it is becoming stable. Here it is becoming stable. right? Here it is becoming stable. Here we can see that. Here you can't see anything like that. Then how can, that's why in the calculated zone, it is going up. But in the observed, it is going down. That we will talk about why, because that is a question, that why it is a dip, why it is showing a dip. First, you need to understand why it is a question, that it is why they are asking that why it is showing a dip. Because according to our calculation, there is no solid reason that we have that oxidation is very easy. Similarly, in case of nickel, same in case of nickel you have. In case of nickel also, what is the electronic configuration? That is 4s2 3d8, right? Now that means cobalt, that means nickel 2 positive, that is going to be, this is 4s2 3d8, this is 3d8. Now 3d8 is not a stable electronic configuration or anything like that. So that is the reason we can say that if 3d8 is not any stable configuration, wait a minute, let me just write it here. Nickel 2 positive, this is 4s2 3d8, this is 3d8. So this is not actually a very stable electronic configuration. If I am saying, if reduction potential is showing a dip, then E naught reduction potential should be low. That means reduction is tough. Again, same thing, oxidation is easy. But here we can't see oxidation being easy. I can't see anything which is showing me oxidation is easy. So that means this is also a very weird behavior, because here you can't see any stability. Here according to this should be there, but here we can't see anything like that. So on the similar ground, cobalt and nickel, we are not able to understand this particular part, that why it is showing so. And third thing is weird is that all of them are below zero. All of them are negative, 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 negative. Only copper has positive reduction potential. Why it is so? So these three things we are going to study in your NCERT, and from where questions are asked. Firstly, why cobalt and nickel, their observed values are different. They are showing a dip here, right? Here it is decreasing, here also it is decreasing. Now ma'am, you will say, ma'am, how it is showing a dip, ma'am? Here it is decreasing, then again, no. According to the observed value, according to the calculated value, it should be here and here, right? It should be here and it should be, wait a minute, it should be here and it should be here. But observed value is lower than what we expect. Why it is so? Why copper is positive? Let's answer these things here. Okay, let's answer these things here one by one. Tell me guys, if you're able to understand firstly what was the question. Okay, let's see. Even if you see this here, that is from copper, you will see is actually showing a positive value, right? Okay, why so? Let's understand. Now for that you need to understand that standard reduction potential depends upon enthalpy of atomization, ionization enthalpy, first and second two ionization enthalpies. This is your enthalpy of atomization. This is IE1, this is IE2, and this is hydration energy, right? So these are the four factors on which it depends. That means the anomalous behavior values that you have for cobalt, nickel and copper, that will be answerable from this one, right? Let's discuss that. Firstly, we saying the stability of half-filled D subshell and the completely filled D10 zinc are related to their value, whereas E naught of nickel is related. Now we are saying that why there is dip in manganese and zinc, that is related to their E naught values. That means that depends upon the electronic configuration, because stable configuration they are going on, that's why E naught value is showing a dip, that I have just showed you here. Okay, that I have just shown you in a simpler manner. I have showed you here that why manganese and why zinc is showing a dip. In a simpler way I have shown you, and they have shown it in a line that why it is showing the dip, right? Okay, then they are saying whereas nickel, whereas now firstly our answer there are three questions that we have: cobalt, nickel and copper. Firstly in NCERT they have answered about nickel, right? So NCERT is not like it's very systematic, you have to understand things here. So here they are telling about nickel firstly. Nickel is related to highest negative delta H. Now the question is why nickel is showing a dip. The reason being nickel is showing a dip is because its highest value, its very high value of delta H, right? That is corresponding to its high value of delta H, that its E naught value get lowered, because it is a summation of all of them. If any of the value is very low, then it will make the other value also low. So here it's not because of the stable electronic configuration. Here it is because of the hydration, very negative value, high negative value of hydration enthalpy of nickel. That is the reason it is showing. So I'll just mark it here. This is the first answer. E naught for nickel is related to its highest negative value of nickel, right? Okay, then wait a minute. This much to acha, we have forgotten. I think where we are. I was thinking that why they have not given answer for other things, right? Let's see that. We forgot about these things now. Then there is unique behavior of copper. Why copper is like having positive value? Why it is so? The answer lies here. Having positive E naught value accounts for its inability to liberate H2. Okay, that we know, but why? Only oxidizing the high energy of this is not. Firstly, the reason is here. These are the consequences. Firstly, I'll tell you about the reason. The reason is that why E naught value of copper is positive, because the high energy to transfer from copper to positive. Why? See, firstly tell me one thing. If I say E naught value of copper to positive is high, if I say E naught value is positive, E naught reduction potential of Cu2 positive to Cu is positive. That means it is very high. Positive means it is high. That means it is positive, right? That means reduction is easy. That means reduction is value is high. That means it wants to get reduced. Reduction is easy. If I say reduction is easy, that means copper oxidation number decrease in will be easy. Copper 2 positive to copper is easy, right? There is decrease here. That means copper 2 positive, it will be tough. Copper 2 positive, it will be tough. Now let's see the electronic configuration. This is 4s1, 3d10, 2 positive is this thing. Now can you see it is actually tough? Can you see it is actually tough? We are not getting converted into, see, when you get converted to copper positive, then to 2 positive. Copper to copper positive, it is 3d10, 4s1, 3d10. This will be 3d10. Then you have to take out electrons from this very difficult part. You have to take out electrons from this 3d10, which is a difficult task. It's not an easy task to take out electron. That's why Cu2 positive is very difficult. That means to take out this electron, you need to give very high this energy. You need to give very high ionization energy here, right? ionization energy needed will be very high, right? So if you see this table over here, in case of copper, the second ionization energy, can you see, to take out second electron, the second ionization energy is very high here. Can you see this for copper? Let me just mark it for copper. Can you see the second ionization energy of copper is quite high, right? Isn't it? Can you see this? Yes, everybody. Second, the take out second electron from copper positive, it's very difficult, right? So you can write it here. Second IE of copper is high. Copper has very high second IE. But the value of hydration enthalpy is not enough to compensate for the high energy that is needed, right? This is what they have written here, that the high energy transform that we need to convert copper to copper 2 positive is not balanced by hydration enthalpy. It is not balanced by hydration enthalpy. This is very, very important. I told you every single reason why it is so, right? Okay. Yes, everybody, tell me. Okay, I'll just write this here as well. Copper positive to copper 2 positive, high IE2, which is not balanced by hydration enthalpy. Hydration enthalpy. This thing is not balanced by hydration. I have just written it in a simpler version. You see, your notes of NCERT will look like this when you study from me, right? Otherwise, how you study NCERT is, okay, copper high energy, then you don't understand anything what is written, you don't evaluate this thing, you just read, okay? NCERT is not about reading, it's about understanding, okay? That's why copper has positive. That's why its reduction is very, very difficult, right? Its reduction is very difficult because the hydration enthalpy that we have is not enough to transform this thing, right? Then what are the consequences of this thing? Can you tell me what are the consequences? Consequences are its inability to release H2 because its reduction potential, it does not see. This also I'll tell you why this is the consequence. Its inability to release H2 from acids, right? Let's talk about this here. We are saying that it does not have the ability to release H2 from the acids. So guys, what we have here is, we have copper, right? We have copper. This is HCl. From acids, I'll have H positive, right? Then what will happen? This is always going to come from acid. Then what will happen? This should be converted to Cu2 positive and then this H2 will be released. That means if I can say here you will have your oxidation, and here you will have the, here you will have the reduction part, okay? Here this is your reduction part. Wait a minute. Okay, this is your reduction part, right everybody? Wait a minute. Right, this is your reduction part. If I say this is the oxidation part, this is the reduction part, that means here this should be easy. If this oxidation is easy, right, then this reduction will be easy. But we know that this oxidation is tough. I am writing it in a very simple language, easy, tough. I am not using difficult languages here. So this is also tough. If this thing is not possible, this is also not possible, right? So that is the reason we are saying. So, or in a simpler way, this is actual fact here, right? But when we say hydrogen has reduction potential 0, copper has 0.34. So the ones that have, the ones having reduction potential lower than hydrogen can take H2 from acids. They can have H2 from acids, right? But the one that have higher reduction potential, that is only copper, that cannot take hydrogen from acids, right? So this is what we have written. Its inability to liberate H2 from acids, only oxidizing agent, nitric acid and hot concentrated sulfuric react with copper, the acid being reduced, right? So we are saying that only in these two cases, only oxidizing agents like nitric acid and hot concentrated sulfuric acid react with copper, the acids being reduced. Then only the acid can get reduced, because they are very, these acids have very high oxidizing nature. If they have very high oxidizing, because see, what we are saying, it is very difficult. What is the problem here? The problem is that it is very difficult to oxidize copper. If you have good oxidizing agent, you can write it. But if good oxidizing agent like H2SO4 and HNO3, then possible. Because then copper's oxidation will be possible, which is actually right now a very difficult task, right? Okay, which is right now we know that it's a very difficult task, but if you have very good oxidizing agent, then it becomes easy. Now I think so, now every single line is clear to you. The general trend towards E0 values occur across series is related to general increase in the sum of first second ionization enthalpy. It is interesting to note that E value for manganese, nickel and zinc are more negative than expected. Manganese is also, then it is not written in the graph. Manganese, nickel and zinc is more negative, slightly more it will be, slightly more negative than expected, right? Now, why manganese and nickel is more negative? That is simply because of the stable electronic configuration. Why nickel is more negative? That is because of the negative hydration enthalpy that we have. Okay, tell me, is that clear? Is that clear, everybody? Yes, Manjula, good morning. I have finished Vedantu Eklavya test series, NEET level, ma'am. I am your new students. I'll come to your class always. Thank you, Manjula. Thank you, previous classes, ma'am, which is so useful, interesting. Thank you, Manjula. Maha is saying, ma'am, to tell you all them to come back. We won't. Okay, that's so sweet. I'll definitely, convey your messages to the team. Right? That's so sweet. That's so sweet. We also miss you all. We also miss you all. That's so sweet. Okay, chalo. Now tell me, don't worry, beta. We are here only. We are no. Gopika ma'am is also teaching. If you know the name of the channel, right? Shreya sir is also there. You can study physics from him. Baswa sir is also there. I am also here, right? So don't worry. The team together, we know that you want all of us not to be clustered but together, but it will soon happen. It totally depends upon your response, right? Okay. Tell me, students, tell me in the chat box. Is that clear? Let's see M3 positive to M2 positive. Now that is the same thing, right? I'll just write it over here. That is the same thing, that if M2 positive to M3 positive is reduction potential is high, that means M2 positive to M3 positive reduction is easy. That means M3 positive to M2 positive will be tough. That means we can say that reduction will be easy if it is high, oxidation is tough. So high reduction potential means reduction is easy and that is tough. Now I'll just change all the things here. I'll just duplicate this thing here. Now this is low, this is yes. Okay. Now if I see this here, if this is low, then M2 positive, this will be tough. Okay, that will be tough, and this will be easy, and this will be easy, right, and this will be easy, and that's why oxidation is easy, right? This is all you have to remember. Rest of the things are same here. Let's see. An examination of E3 positive values shows varying trends. The low value of scandium reflects. Now first is why there is low value of scandium to scandium 3 positive. Guys, tell me, if I say scandium to the stability of this which has noble configuration. Acha, scandium 3 positive to scandium 2 positive has low value. That means its reduction is difficult, its oxidation is easy. That means scandium 2 positive to scandium 3 positive is a easy task, because scandium is what? Scandium is 4s to 3d1, and this is 3d1 and this is 3d0. So it is getting converted to a stable electronic configuration. That is why it is having a low value. So this is what I told you. If reduction potential is low, that means oxidation is easy. As simple as that, right? So this is what they have told you here. A high value of zinc is due to removal of an electron, and I'll just write it here, the things that they have written, right? So first is low value of scandium, right? From where, which is the highlighter that I should use here. Orange one I'll use. Low value of scandium we have, right? That's the first thing. Then highest value of zinc. Now can you tell me why you have highest value of zinc? Anyone of you can tell me why it is having the highest value for the zinc, right? Why it is having high value for zinc? This one which I am deleting, because that I have already written there. So I'll just delete this thing. A minute. Yes. Okay. High value of zinc is because of what? Because if you see zinc, wait a minute. Zinc 3 positive to zinc 2 positive, it has high value. That means the reduction is very easy. That means zinc 3 positive to zinc 2 positive is quite easy. But zinc 2 positive to zinc 3 positive, if this value is high, wait a minute. If this value is high, reduction is easy, oxidation will be tough. Yes, oxidation means zinc 2 positive to zinc 3 positive, that is oxidation is tough, that we have written there. So oxidation is going to be quite tough here. Now can you tell me why? What is the reason behind that? Can you tell me why oxidation is going to be tough here? Can you tell me why oxidation is going to be tough? Simply because this is zinc is 4s to 3d10, zinc 2 positive is 3d10. So you can just write this here. This is nothing but it is 3d10, right? And this is 3d9. So obviously this is going to be tough. Okay, I'll just write it like this. Okay, tell me, is this getting clear? I am just doing this from the electronic configuration. Is due to removal of an electron from the stable D10 configuration, the comparatively high value of manganese. Now why manganese is having high value? iron is having low value, right? Then again, it's based on the similar thing, right? High value of manganese, high value of manganese, low value of iron, low value of vanadium, right? Same thing we are going to do here. I'm just going to write it in the rough, I'm going to write it. If you talk about manganese, right? If manganese has high value, that means manganese 2 positive to manganese 3 positive will be tough. Manganese 2 positive is nothing but 3d5, 3 positive will be 3d4, so definitely it is going to be tough, right? Then if you talk about next is iron, iron is having low. Why? Because iron is having low value, that means the oxidation is easy. Fe2 positive to 3 positive is easy. Fe2 positive is nothing but 3d6, right? Fe is 4s2 3d6, Fe2 positive is 3d6. This will become 3d5. So it is getting converted into a stable configuration. So that is the reason it is easy, right? That's why it has low value. Then talking about vanadium. Vanadium, if you see, vanadium 2 positive to vanadium 3 positive, because it has low value, so that means it is going to be easy. Vanadium is nothing. What is vanadium? Tell me. Vanadium is 3d3, 4s2 3d3. You take out 2 electron, it will become 3d3. You take out one more electron, it will become 3d2. But here na reason is different. Let me tell you. Reason is not here in case of vanadium. Let me tell you. In this case, comparatively, this is important, okay? This thing is important. Low value of vanadium, so I'll just write it with a different pen. I'll write it with a different pen, right? I'll mark it with a different highlighter here, right? Low value of vanadium, right? That is related to the stability of V2 positive. Why V2 positive is more stable? Because of its half filled T2G level, right? That is the reason its value is low. Because if you talk about V2 positive to V3 positive, right? If we are saying that its value is low, right? Whenever the value is low, this becomes easy, right? But here in this case, what exactly happens? First thing is, this is 3d3, this is 3d2, right? So this is stable due to its this is very important thing, okay? Remember this. This is stable due to its T2G level like this. T2G level means this thing. In CFT, we fill 1, 2, 3 electron. Ma'am, if this is stable, this conversion is difficult. That means if this conversion is difficult, this should have low value. But you know what? This is what is important for you to remember. Here they have written, they are not saying it is, reason is that V2 positive is more stable. V2 positive is more stable, that is correct. But this stability is observed experimentally based on so many values that you have for ionization enthalpy, enthalpy of atomization, based on all these, because this has, vanadium has very high, it is the highest enthalpy of atomization, right? So because of its highest enthalpy of atomization, ionization energy, all the factors will contribute here. The reason is not here, it is directly written, what students will feel, the comparatively low value of vanadium is related to stability of V2 positive. Stability of V2 positive is there, that is correct. V2 positive is stable because of its T2G level, right? Because if you fill the electrons like this, 3d3 are more stable because it is giving rise to a half filled. If you fill the electrons in CFT, where you have, let's say 1, 2, 3, 1, 2, 2 electrons, if you fill, that is not stable. 3 electrons you fill, that is more stable. So definitely that is correct, that its T2G level is giving V2 positive more stability. But because of other factors, right, the value of vanadium will become less. Okay, everybody, right? Yes? Done. Yes. Definitely, yeah, you can watch this for JEE mains as well because NCERT is same. NCERT, I to definitely recommend to JEE main students as well, right? So let's talk about this is done, guys. Now let's start off with other parts here, right? Everybody, this is done. Now let's start off with stability of higher oxidation. Difficult part we have done. Now this whole page is very, very important. This whole page is very, very important because so many important things they have given you for the oxidation. Till here na, you will feel that things are getting confused again and again, different things they are saying, but after this very smooth things are going to happen. But till here, before magnetic properties, things are going to be little confusing, and these are the things, that's why I asked the students to read the chapter, right? Let's see. Let's see, everybody. Ready, 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 ready. Let's see this, everyone. Let's see this. Trends in stability of higher oxidation state. The stable halides from 3D series of transition elements. There are stable halides as well. Highest oxidation state are achieved by TiX4, this and this. Now, if you see the halides here, we are saying highest oxidation states in case of halides are achieved by titanium, vanadium and chromium. Manganese, iron, they are not achieving their highest oxidation states. Highest oxidation states are achieved by Ti, vanadium and chromium. +7 state of manganese is not represented in simple halides. That means +7 state is not represented in the simple halides, but MnOF is known, and beyond Mn, no metal has trihalide except for Fe and this. Now what we are saying that Mn is not showing +7 oxidation state here, right? But there is an oxide that is, this is very important, they can ask you directly. This is very, very important. They can ask you this directly, which is that oxide in which Mn exists in a high oxidation state. Let's try to find out its oxidation state. X minus 6 minus 1 is equals to 0, that is X is equals to +7. So here Mn is in the +7 oxidation state. That means in case of pure halides, it does not exist in the highest oxidation state. But in case of Mn2O, MnO3F, this is important, guys, right? That's why I'm marking it here, right? This is important, okay? So MnO3F, that is that kind of halide which is oxohalide, right? That is known where the oxidation state of manganese is +7, even though there is one halide that is connected to it, right? Beyond Mn, no metal has trihalide except for this. If you see beyond Mn, only this and these trihalides are possible. Other trihalides you will not see here, right? Other trihalides are not possible, right? Beyond Mn, no trihalide is possible. So if I am writing something, wait a minute, you know what I'll do? If something is like not important, not that important, I'll just underline it simply. Beyond Mn, no metal has trihalide except for this and this, right? The ability of fluorine to stabilize highest oxidation state is due to either high lattice. Now, why fluorine is able to stabilize the higher oxidation state? Higher oxidation state, ability of fluorine to stabilize higher oxidation state is due to either high lattice energy that is needed in case of COF3, or higher bond enthalpies that are needed, bond enthalpy, for higher covalent compounds like VF and CR, right? So that means we are saying in these cases, right, which are covalent compounds, what you will see that here it is because of higher bond enthalpies that they have high oxidation states, right? they can stabilize this, that means good bonds are formed here, right? But in this case, high lattice energy is needed. That's why higher oxidation states are shown here, because high lattice energy is needed in case of COF3 and FeX3, right? Although if you talk about, now we are talking about, if you talk about V5 positive is represented only by this VF5, the other halides however undergo hydrolysis to give oxo halides. Now this is also very important, that these will undergo hydrolysis to give oxo halides, that is VOX3, right? These other halides will undergo hydrolysis, right? So other halides undergo hydrolysis to give oxo halides, that is VOX3. Another feature of fluoride is their instability in the lower oxidation state. Like what we will see, lower oxidation states are not stable here. Only higher oxidation states are stable here, right? Like VX2, they are not stable. The same applies to CUX. If you see, CUX is also not stable. This is also not stable. This and this is unstable halide here, right? That is also another feature. On the other hand, Cu2 positive halides are known. Now, this is a very important question, that halides in the lower oxidation states like VX2, CUX, they are not stable, right? And CUX is, you will see, this is the lowest halide which has oxidation state of +1 here. Now, why it is so unstable? What is the reason behind that? And that question is very, very important, right? That why is Cu2 positive? It is not at all stable. What is the reason behind that? Right? What we are saying here, right? So what we are saying, same applies to 6. On the other hand, all Cu2 halides are known except for iodide. Now, first thing we are saying that, CUX is not stable. Then we are specially saying that Cu2x is stable, but this is very important and repeated question. But Cu2i is not stable. It does not exist only, right? Cu2 positive halides are known except for iodide. What is the reason, right? Now, what exactly happens when you have Cu2 positive and I negative? It is getting converted to Cu2I2 and it releases I2. Instead of existence of Cu2 positive and I negative, they should make a compound, that is Cu2I, but they don't do so. They don't make a compound. Instead, this is converted to Cu2I2, where copper is +1 and wait a minute guys, state, and it was basically Cu2 positive. This is -1, this is 0. So it is basically acting as an oxidizing agent here. It is oxidizing I negative to I2, right? It is oxidizing I negative to I2. That is why Cu2I does not exist, right? So this is one very, very important, wait a minute, what I can see, right? So this is a very, very important question that you must know, okay? Then next, let's see what we know. However, many copper positive compounds are unstable. Now we are saying that Cu2 positive ions are stable, right? But Cu2I does not exist because of this particular reaction. That is a one case of Cu2 positive. Now we are saying that, but there are also cases where Cu positive is also not stable. Let's see how. However, copper 1 compounds are also unstable in aqueous solution. It's not like copper positive ion. So what we should know, copper positive is 3D9, 3D10. Copper 2 positive is 3D9. So this justification still we are able to understand that copper 2 positive is getting converted to copper positive, right? Okay, that's not a big deal. Okay, that we are able to understand. But why this is happening? This is 3D10, this is 3D10, right? This is 3D10, this is 3D9. Now, why it is being dissociated to 3D9? However, many copper 1 compounds are unstable in aqueous solution, undergo disproportionation. That's a very, very famous reaction, that it undergoes disproportionation. But the question is why it is undergoing disproportionation like this. Okay? Why it is undergoing disproportionation like this? That's a very, very important, two very, very important reactions, right? Now what we are saying, the stability of Cu2 positive. Now why Cu2 positive is more stable even though it is 3D9, even though its configuration is not stable? But is there any problem in the connection or what? Is it fine now? Am I audible to all of you or not? Right? Tell me no, let me know in the chat box. The stability of Cu2 positive rather than Cu positive is due to much more negative delta H hydration of Cu2 positive. So what we are saying, why Cu2 positive is more stable? Cu2 positive in aqueous medium is more stable because in aqueous medium, when Cu2 positive is in the aqueous medium, it releases more amount of hydration enthalpy as compared to Cu positive, right? Hydration means when it is in the water. So that's why Cu2 positive becomes more stable, right? Stability of Cu2 positive rather than this is due to more negative delta H hydration of Cu2 positive than Cu positive. That is the reason that this disproportionation reaction is taking place. That is the reason that this disproportionation reaction is taking place, right? Okay, everyone? Which more than compensates for the second ionization enthalpy of copper, right? So now it will compensate with the second ionization, because I told you that second ionization enthalpy, if you remember, I have told you somewhere here, right, that second ionization enthalpy of copper is very high, right? And if you talk about copper positive ions, they do not, what we are saying, when we transfer Cu to Cu2 positive, it is not balanced by the hydration enthalpy that is there. But in case of when Cu2 positive ions are already there in the solution, right? Okay, then disproportionation of Cu positive takes place, because in that case the ionization enthalpy is balanced by the negative hydration enthalpy. Okay, now we will see for oxygen. If you see for oxygen, the trend is entirely different. In case of fluorine, manganese was not showing +7 oxidation state, only with halides. But in case of oxygen, manganese is showing +7 oxidation state, right? That means something different is there. The ability of oxygen to stabilize higher oxidation state is demonstrated in the oxides. High oxidation number in the oxides coincides with the group number. So what we are saying, highest oxidation state. So here what we have, highest oxidation state is +4, this is +3, this is +5, this is +6, that is +7. So can you see that here till manganese, group number is 3, it is 3, 4, 4, 5, 5, 6, 6. Can you see that the group number is coinciding with the highest oxidation state? This is what they are writing here, right? Then beyond group 7, no higher oxidation of iron above Fe2O3 are known, although ferrates are known. Now this is an important line, that iron, if you see, even in oxides, this is existing in +3 oxidation state, this is the mixed oxide. If you see, these are the mixed oxides. Okay, I'll just name it here. These are the mixed oxides. Okay, these are the, wait a minute, these are the mixed oxides. These are mixed oxides, they are not normal oxides, right? if you see this thing here, this is having +2 oxidation state. So we can say that iron and beyond, right, especially for iron, +3 oxidation state is the maximum oxidation state. No higher oxidation state above this is possible, but we are saying that, although ferrates means this thing, although ferrates, that is this thing, is possible. Ferrates are formed in alkaline media, but they readily decompose to Fe2O3 and O2. So ferrates are possible. If you see what is the oxidation number of iron in case of ferrates, let me just write it. This is x minus 8 is equals to -2, so x is equals to +6. So in case of ferrates, the oxidation state of iron is +6. Okay. So this they can ask you, out of the following which does not exist. So ferrates exist, right? Fe2O4 2 negative exist, are formed in alkaline media and they decompose readily into Fe2O3 and this. Besides the oxide, oxocations stabilize. Now oxocations that you have, they stabilize 4, titanium 4 positive, vanadium 4 positive, vanadium 5 positive. So you have, beside the oxides also, you have oxocations. Now when you talk about oxocations, there are some oxocations like these. They stabilize high oxidation states. Now if you see vanadium, right, vanadium 5 is also possible in VO2 positive, VO, then 2 positive on the superscript, then TiO 2 positive is there, right? Then we say the ability of oxygen to stabilize higher oxidation state exceeds the fluorine. Now this is a very famous question, that why? This is a very famous question from your NCERT directly. Ask it why. Why it is so? Why the ability of this is higher? Because it is said that the ability of oxygen to form multiple bonds to metal explains its superiority. Because oxygen can form multiple bonds, that is the reason it has ability to show higher oxidation state as compared to halides. Now we are talking about that how in the covalent oxide, that is MnO7, manganese is tetrahedrally surrounded by oxygen including MnO-Mn bridge, right? The tetrahedral MO4 N negative are known for vanadium, chromium, manganese and this. So basically we are saying in case of Mn2O7, do you remember Mn2O7? This is a tetrahedral. How it is tetrahedrally done? Let me just show you Mn2O7. Let me see if it is already there. No, it is not there. So let me just show you Mn2O7. This is Mn2O7 is what? MnO-Mn 1, 2, 3. 1, 2, 3. Right? Actually, it must be like this. Tetrahedral, na? So it must be like this. Okay. So this will be double bond O, 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 double bond O. Right? This is the structure of Mn2O7. Right? Okay. Manganese is tetrahedrally connected. This is one tetrahedral, this is next tetrahedral, so it is tetrahedrally connected. Others are the tetrahedrals of MO4N negative. Now if you talk about MO4N negative, there can be different examples. Let me write it there, right? So MO4, if you put vanadium here, if I put vanadium here, this is MO4, this will become, this is 5, so it is +5 minus 8, this will become 6, 7, 8. So it will become -3. So you will write vanadium O4 3 negative. Then chromium O4, this will be, chromium is what? Chromium is in 6, 6 minus 8 is -2. Manganese plus 5, manganese 5, 5 minus 8, again it is minus 3, manganese O4, this is 3 negative. Manganese, if it is in oxidation state 4, it will be minus 2. If manganese in oxidation state, acha 6, this is 6. Acha, chromium is in 6, this will be minus 2, minus 2. If it is in 7, 7 minus this will be 8. MnO4 negative. So these are the ions that we are talking about. Right, everybody, tell me. Okay? Yes, everybody. Then the question is, how will you account for this particular? How would you account for increasing oxidizing power? Right? Tell me. This is due to the increasing stability of lower species to which they are reduced. Right? Okay? Like here, basically this is in vanadium 5 positive. This is chromium 6 positive. This is manganese 7 positive. And the stability of lower oxidation state of manganese is higher than chromium, than vanadium. Right? And that's how we have this. Right, everybody? Chalo. Then we have next thing, that is chemical reactivity of E0 values. Let's talk about that. This is basically, we are talking about that which will reduce or oxidize something, all these things we are talking about here. Right? Okay. Done, everybody? Done, everyone? Let's talk about this now. Let's talk about this. Chemical reactivity, the transition metals. We are saying the transition metals vary widely in their chemical reactivities, right? That means their reactivity is different. Many of them are sufficiently electropositive to dissolve mineral acids, although few are noble, that is, they are unaffected by single acids, right? The metals in the first series, with the exception of copper, are relatively more reactive. Copper is not reactive, others are more reactive and are oxidized by H positive. That means, this is an important line, that in the case of exception of copper, others are first series elements with the exception of copper. You can just write the full line here. First series with the exception of copper are relatively more reactive and are oxidized by H positive. That means they releases H2 gas, right? Okay. Metal with oxidizing agents like H positive ion and now we are saying that though the actual rate at which these metals react with oxidizing agents like hydrogen is sometimes slow. Actual rate at which they do so is actually sometimes low. For example, titanium and vanadium in practice are passive. Now this is very important point, very important point. Except for copper, according to the reduction potential values, others should liberate H2. But titanium and vanadium are passive to dilute non-oxidizing acids at room temperature. That means if you have other acids which are non-oxidizing, right, titanium and vanadium are not interested in reacting with H positive. E0 value shows a decreasing, if you talk about the E0 value, indicate a decreasing tendency to form divalent cation across the series. If you see the E0 values here, that is this one, they are decreasing, right? If you see this one, that is decreasing here. That means what we want to say, that actually what is happening, if E naught value is here increasing, if I don't look at the exception, if I look that this is straight, right? If E naught value is increasing, that means the tendency to get reduced is becoming high. That means the tendency to get oxidized is becoming low. Tendency to get reduced is M to M2 positive. This is becoming high because this is, wait a minute, tendency to get reduced, that means M2 positive to M is very high. Opposite means M to M2 positive is becoming low. That means the tendency to form divalent cations is becoming low. This is what they are telling, that if we take a general value here that they are generally increasing, then their tendency to get reduced is also becoming less, right? Divalent cations tendency to form is across the series is becoming less. General trend towards less negative E naught values is related to general trends. General trend we are talking about. What about the general trend here? Right, the general trend towards less negative E naught values related to increase in sum of first, second ionization enthalpy. General trend is less negative value of, that we are saying if something has less negative value of E naught, that means less negative value of E naught means its reduction is very low. I'll just tell you here, right? What do you mean by less negative value? That means reduction is easy or tough? Less negative value, beta, reduction is easy or tough? That means reduction is tough. Oxidation is easy, right? Oxidation will be easy. So we are saying that less negative value of E naught, that means we are saying that reduction is tough and oxidation is easy, is due to increase in the sum of first and second ionization enthalpy, right? If sum of, just we are saying that it's a less negative, wait a minute, less negative is increasing or decreasing? Arre, my bad. Arre, less negative value means what? Less negative value means if something is -5, then it is -2, so it is less negative. That means reduction potential is increasing. So we are saying reduction potential increases, that means oxidation potential decreases. That means M2 positive is tough. Why? Because first and second ionization enthalpy, their sum is high. Why reduction will be, why oxidation will be tough here? Beta, yes, it's a live session, right? So why the reduction values, if I talk about why less negative means what? Tell me, what do you mean by less negative? Less negative means reduction potential is high, oxidation potential is no. That means M to M2 positive, that means oxidation is tough here. That is the reason ionization enthalpy values, first and second, they have increase in that corresponds to this thing. It is interesting to note that E naught values for manganese, nickel, zinc are more negative than expected. We have seen this here from the general trend, whereas the stability of half filled in manganese and completely filled in zinc are related to their E naught values. For nickel, it is related to the highest negative. This we have already seen, right? An examination of E naught values of redox couple, that if we see E naught value of redox couple, that is this one, shows that M3 positive and this ion are strongest. Now this is very important, that how come? Now you have to understand that how we are saying it again and again. Now if I am saying that this and this ions are strongest oxidizing agent, how am I saying that? If I say, right, these are high, like they are very good oxidizing agent, that simply means that M3, Mn, if I say that some metal is a good oxidizing agent, M3 positive, that means it itself wants to get reduced. That means M3 positive to M2 positive is easy. Now in case of manganese and cobalt, it's easy. Now why? Because manganese 3 positive is nothing but it is 3D4. and cobalt 3 positive. If you see, cobalt is nothing but 4s2 3d7. If you take out 3 electrons from here, wait a minute, this oxidation couple, wait a minute, table 4.2, let me just see table 4.2, right, where is table 4.2, it is 4.4, wait a minute, yes, this value, na, this is the table 4.2, okay. Now in this case, in this table, what we can see, this is titanium Tv Kar Man Fi Ko. Man Fi Ko. Now if you see in these three cases, highest value of reduction is what? Here this is for manganese and this is for cobalt and manganese. Manganese corresponds to its, manganese has very good reduction potential. That means manganese 3 positive to manganese 2 positive. Reduction potential easy means, reduction potential easy means reduction is very easy. Right? Manganese 3 positive to manganese 2 positive is very easy. Why? Because of stable configuration. Right? But in case of cobalt, cobalt 3 positive to cobalt 2 positive. Is it easy or not? Let's understand that. This is 3d6. If it gains 1 electron, it will become 3d7. Right? It will become 3d7. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. So that means it is not related. Cobalt is not related to the electronic configuration. Cobalt is related to maybe hydration, enthalpy, right? These things. It is not related to electronic configuration. That I will just write it here. Right? So see, like this chapter is like that. Only you have to go through it in detail, because these are the things that they focus on. So cobalt and these are very good oxidizing agent only because of their values are very high. Because strong oxidizing agents, reason being their high E0 values. Their E0 values are very high, right? As you can see from the table. Now if you talk about titanium, vanadium and chromium are strong reducing agents. Now again, if I show you that in the table here, right, can you see titanium, vanadium, Tv? These are reducing agents and these two are oxidizing agents. Because here their reduction, if reduction potential is high, that means its reduction is easy. That means it would want to get oxidized and reduced and get oxidized something else, right? If here reduction potential is low, that means their oxidation potential is high. That means here oxidation is easy for them. They are very good reducing agent. So that's why we are writing it in that value. See from the tables, can you see table is somewhere else? They are writing it somewhere else, right? Students though, they will be like, okay, titanium, but it is actually there in the table, right? That these three things, you can say titanium, vanadium and this are strong reducing agents. Very important, right? That they are reducing agents and they will liberate hydrogen from dilute acid, because they are very good reducing agent. They can easily get converted to, they can easily get reduced, so they can easily oxidize something else. Oxidize means oxidation number is very good. I'm so sorry. I'm so sorry. Sorry. They are very good reducing agent. That means they want to get oxidized themselves. So easy oxidation is possible. If oxidation is easy, that means reduction is also easy, right? So Cr2 positive, titanium 2 positive, chromium 2 positive, they are very good reducing agents, right? Okay. Yes, everybody tell me. Clear? Let's see these two questions as well, right? First thing is, for the first row transition metal elements, E naught values are not regular, which are explained from irregular variation of ionization enthalpy, sublimation energy, which are relatively much less for manganese and vanadium. That is why there are irregularities here that you will see. Right? Okay? Sure. Tell me guys, now do you want to take break? How much time? 1 hour 30 minutes we have studied, right? Yes. And too much so we have studied about this one. That was a tough part of DNF block. Like these all pages that we have done, right? See, from the tables there are so many important things that I have marked. You can see for yourself that there are so many important things that I have marked for you here, here. Reason being, there are things important that are given. See, so many things I have written on the side also, because there are important things that are given here, right? Now after this we'll start with magnetic moment, but before that I would like to give you break, right? Because magnetic properties we'll talk about. This is quite easy, but here then formation of colored complexes, these colors and all these are important, right? Then we'll talk about all these properties. I think we'll be able to do, right? Then we'll start with important transition elements, compounds, right? Okay, tell me. Yes, students? Break everybody. Yes, ma'am. Ma'am, if the reactant Cr2 positive value is 6, then in the product if 1 mole of Cr is there, then we have to consider 3 or 6. You're talking about the oxidation state or what? Oxidation state. Ma'am, Cr2 value is 6, then the product if 1 mole of Cr is there. Beta, do you remember we have done redox reactions? There we discussed about the balancing of reactions. Okay? So always the charge has to be equal here. Okay? Overall charge has to be equal here, no matter what. Right? Okay? Charge should be equal. There cannot be different charges here. Charge has to be equal there, right? So for example, not charge, the number of electron gain and loss should be equal. For example, here I am saying this is plus 4, this is plus 6, right? This is plus 2 and this is 0. I can see that here in case of oxidation 2 electrons it will lose, and in case of reduction 2 electrons it will gain, because the difference in the oxidation state is 2, right? The difference in the oxidation state is 2. Plus 4 to plus 6 is 2, plus 2 to 0 is also 2. So that's why electron gain and lost will be 2, right? I hope so. This thing is what you are asking, is it? You must be thinking, ma'am, here it is plus 4, ma'am, here it is plus 6. So what the charge should I consider? Charges, oxidation states are different here, right? And that depends upon the stoichiometry as well. You can't consider here plus 2 charge. You have to consider plus 4 because stoichiometry is important factor here. Okay? Chalo. Okay, then I'll just now give you break, right? Let's take a break and we'll join back after how much time? After 15 minutes? Tell me. 15-20 minutes break, lunch break I'll give you, right? Easily, right? Relax your mind. After that we'll start with the rest of the part. Hi, motivating minds. Welcome to the class. Welcome to the class. Yes. Tell me how much time break you need, because lunch break is also there, because after that I'll teach for 2 more hours, right? So accordingly I'll give you the break. Tell me. ठीक है जी, चलो. Okay, so now after this we are going to start with magnetic properties, right? So yes, let's see. I'm giving you break here. Yes, how should I write break? Shall I write it here? Because other pages I can't erase. Okay, I'll be giving you break, right? How much time break you need? 10 minutes, 20 minutes, how much time? Tell me. How much time break you need? I think the class will resume at what time? At 2 p.m. ठीक है? At 2 p.m. the class will resume. 15 minutes break I am giving you. Right? You can relax your mind in between and I'll see you after that. Right? Okay guys, and I'll see you all after the break. By the time, relax your mind and see you all. Yes. Okay, so I'll see you all. Then now I'm ghosting you. Okay, let's see. Hello. Hello, hi everyone. Yes, everyone, back to the class, students. Yes, do let me know if I am clearly visible and audible to all of you or not, so that we can do the rest of the part here. Yes, students, do let me know about it so that we can do the rest of the part. Let's start. Not daily classes. I don't take like the daily classes on this channel, but I inform you on my Telegram channel, Chem Catalyst Diksha, when I'm going to take the class. So now, right now, NCERT series is going on where I'm taking DNF block class, and P block I'll take after this. After completing this one, I'll take P block classes. Right, everyone? Let's do that. Yes, students, let's do this, everybody. So, now let's start with this. What we have is magnetic moment, right? So, when you talk about magnetic moment, right, this we have done in so many places. Basically, there are two type of things. First is here you don't have to read out NCERT that much, right? Here reading NCERT is not that important because general things are only given. Diamagnetic and paramagnetic is there, right? Diamagnetic is which is repelled by the applied field, while paramagnetic is attracted by the applied field. Okay, wait a minute. Yes, diamagnetic is repelled by the magnetic field and para is attracted. In diamagnetic you have no unpaired electron, and in paramagnetic you have unpaired electrons. At least one unpaired electron should be there. That means it is paramagnetic in nature. And there is a third category that is called as ferromagnetic, that is attracted very strongly by the magnetic field. Para is attracted, but ferromagnetic is attracted very strongly by the magnetic field. Ferromagnetism is an extreme form of paramagnetism. Many of transition metals are paramagnetic in nature because they have unpaired electrons, right? So this is quite easy. This you don't have to remember. Contribution of orbital is effectively quenched and hence there is no significance. Just remember this one. What is not important for you, the general things are given regarding this formula. Just remember this formula, that is in Bohr magneton, that is called as Bohr magneton Bm, right? This is the formula that you have where n is the number of unpaired electron, mu is the magnetic moment, right? Now we are saying that as magnetic moment increases with increasing number of unpaired electron, more is the number of unpaired electron, more will be the magnetic moment, right? Observed angular momentum gives a useful indication about the unpaired electrons in the atom. The magnetic moment calculated from the spin only formula is those derived from the some ions. First row are given in the table 4.7, right? What is observed, what is calculated? Can you see observed, calculated is almost same, right? So we can see that observed and calculated is same here. So we'll focus on the calculated one, how observed one, how it is done, right? So just remember that always this thing is what you have to remember. For one unpaired electron it is 0, for 2 it is 1 point, for 1 it is 1.7, 2 it is 2.7, 3 it is, you can write it as like this, I'll just write this here, 1, 2, 3, 4, 5, right? This is 1.7, this is 2, 3, 4, 5, put point. This is 8, 8, 9, 9. Okay. What I am saying, put 1 point, 2 point, 3 point, 4 point here. This is 7, 8, 8, 9, 9, and that is going to be your answer for magnetic moment here. You don't have to do anything here. Can you see? We have not done anything here. All we have done is we have just solved it here. So in a very simple manner, right? This observed magnetic moment gives useful indication. The magnetic moments calculated from this, the experimental data is this thing, right? Okay. So how do you calculate observed and calculated magnetic moment? That is entirely from the number of unpaired electrons. See, scandium 3 positive. Electronic configurations you must know, right? Those who are also like, ma'am, how do you define the electronic configuration? That I told you in the last class, that you must know the, let's say cobalt. Cobalt is 27, so it is 4s2 3d7, right? Let's say nickel. Nickel is 28, so it is 4s2 3d8. You take out 2 electrons. Electrons are always taken from 4s first and then 3d, right? And in case of chromium and copper, chromium is 4s1 3d5 and copper is 4s1 3d10. So these are two exceptions that we have. Rest of it is same. Okay? Rest of it is same. Right, everybody? Rest of it is same that we have, that I have already told you, and based on that you can calculate the magnetic moment, right? Okay. And magnetic moment based questions are asked like so many times. This is one of the most important questions, yet easy one, right? This is not even difficult that I tell you, oh my god bacha, this is so difficult to answer. This is so simple that I don't have to invest more time here. This is so simple. You just have to know the electronic configuration from scandium to zinc. Then you take electrons from 4s first, then from 3d. Accordingly, let's say you have 3d5. So always remember this is your d, right? Okay. This is d orbital 1, 2, 3, 1, 2, 3, 4, 5. Okay. You want to fill 5 electrons, 1, 2, 3, 4, 5. So it means 5 unpaired electron. You want to fill 6 electrons, 1, 2, 3, 4, 5, 6. You want to fill 7 electrons, 1, 2, 3, 4, 5, 6, 7. So it is 3 unpaired electrons. So for 7 it is 3, right? Then you want to fill, let's say 8. 1, 2, 3, 4, 5, 6, 7, 8. You have 2 unpaired electrons for 8. Right, so what we are doing here, in this case, till here, the number of electrons in D is the unpaired electron. So if you see this here, till here, the number of electrons in D, N is number of electron in D. After this, N is 10 minus number of electrons in D, right? So 10 minus 8 is 2, 10 minus 9 is 1, 10 minus 10 is 0. Accordingly, you can calculate the number of unpaired electrons here as well. Tell me, is that clear? Right, so quite easy question. Spin only magnetic moment of M2 positive when cobalt is 27. Cobalt is nothing but 4s2 3d7, right? Cobalt 2 positive is 3d7. So number of unpaired electron is 10 minus 7, that is 3. So mu is going to be 3.8 is the correct answer here. So simply you can calculate like this. Tell me everyone, is that clear? Now let's move towards formation of colored complexes. Now I can see your interest again going down. So I think I'll have to cancel the lectures that I thought I'll take. Okay, I'll see. I saw even in the last lecture how many students you have commented. So this is what I was telling you even in the last previous classes. Okay. Charlene is saying, ma'am, organic chemistry, please. Okay, Charlene, thank you, ma'am, for coming back. Thank you so much, ma'am. Ma'am, where you were, what happened to you? Ma'am, we miss you. That's so sweet, right? So I can see there are students who are also commenting. I'll see what is the love that you give to us, right? Otherwise, though, it's not possible for us to come back, right? Okay, because your efforts also matters a lot. Chalo. Now let's understand formation of colored compounds. Very good afternoon, very good afternoon. So let's see formation of colored compounds. When an electron from a lower energy d orbital is excited to higher energy d orbital, we are saying when you have an electron, so if you remember CFT diagram, it is 1, 2, 3, 4, 5. There is splitting of d orbitals, right? We know that if electron is present here, then it will get excited to the higher energy level and get excited here. So that is lower energy to higher energy level. The energy of excitation corresponds to frequency of light absorbed. So it is absorbing some energy of light which is having some frequency mu. Now we are saying that that corresponds to a frequency which is being absorbed. Now this frequency generally lies in the visible region. This frequency that we are talking about is lying in the visible region. Colored observed corresponds to complementary color of the light absorbed. Now we are saying the color that I can see is actually complementary. For example, this is observing a color that is red. So it will give me, I will not see red color. I will see the complementary color of this one, right? I'll show you how. For that, we must know a color wheel. Let's write that. Color wheel, that will be 1, then this thing, okay, then this thing. Now we will see how to draw color wheel. Just draw this wheel and write Vibgyor, okay? VBGYOR, VBGYOR, right? So firstly I'll write violet here. Violet is this one. So firstly I'll write violet, okay, right? Firstly I'll write violet. After violet I have B, Vib, B, that is for blue, right? I'll write blue here. Then I'll have green, then I have yellow, right? Then I have yellow, then I have yellow. I can also write it differently here so that, you know, we can also remember this thing. Okay, I'll just write yellow like this, okay, so that it is also visible. GYO, O is orange, right? Then there is red, right? Now you will see they represents the complementary color of each other, right? It's not always true, but in most of the cases you will see it's true that if blue color is absorbed, then the complementary color orangish yellow or orangish red will be given. If violet color is absorbed, complementary color that is yellow or greenish yellow or orangish yellow will be seen. Okay, that is the complementary. So color observed corresponds to the complementary color of the light absorbed. The color that is absorbed, corresponding to that you have complementary color. The frequency of light absorbed is determined by nature of ligand. Now we are saying, this is an important point, that the frequency of light absorbed is given by nature of ligand, right? Now how it is given by nature of ligand, tell me. But just see, if there is a very strong field ligand, in a strong field ligand the gap is very high, this gap will be very high, so frequency absorbed will be very high and corresponding to that color will be given. If this is a weak field ligand, it is very less gap is there, so frequency absorbed will be very less, right? So it depends upon what is the ligand. Then we say in aqueous solutions, where water molecules are ligand, the color of ions observed are listed. Now in aqueous solution, now this is a very important chart. Okay, if you see, high level questions are asked from here, right? Based on the colors, high level questions are asked from here. In NEET till now colors, that many questions are not asked, but in JEE this question has been asked in JEE 2025. So in NEET also you can expect the same, because the conducting agency is same, guys, right? Okay, and the level is also same, right? So this is what you should remember. This is already your previous year question of JEE, right? So this can easily be repeated, right? So those students who are thinking of skipping this, you will be doing a big mistake here, right? So colors of some first row transition elements from left to right are given to you. Let's see that. Okay. Scandium and titanium is titanium 4, they are colorless because it is D0, right? Then if you talk about zinc is also D0, that is why zinc is D10, right? So we know that, always remember that in this case, if there is no electron, all the electrons are paired here. Let's say in this case you have things like this. It is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That means you will not have any electron jumping to this position because there is no position that is there where it can land in the higher energy level. That means in case of D0, or D10, no DD transitions are possible, right? In case D0, no DD transitions are possible. That is why they are going to be colorless, right? They will not have any color. So that is why if you see scandium here, scandium is what? Tell me. Scandium is actually 21, right? So if you take out 3 electrons, it will become 3d0. This is 22, that is nothing but 4s2 3d2. After taking 4 electrons, it will become 0, so it is 3d0. Similarly, scandium is also the same. It is 4s1 3d, 4s2 3d1. So you take out electrons, it will become 3d0, right? Similarly, in case of zinc, what you have? In case of zinc, you have 4s2 3d10, right? You take out 2 electrons, it will become 3d10, that is 0, right? This is atomic number 30, right? Others are not 0. Let me just write down the electronic configuration of others, right? Okay, let me just write down the electronic configuration of others. What is titanium? Everybody tell me. Titanium is what? Titanium is 4s2 3d2. So take out 3 electrons, it will be 3d1. I'll just write it down in a purple color, right? Okay. So why to do that much, hai na? Titanium is 3d2, 3d1. Vanadium is nothing but Tv, that is 3d3. 23 atomic number, it is 23. You take out 4 electrons, this will become 3d1, right? Vanadium 3 positive is, you take out 3 electrons, 4 electrons will become, this will become 3d2. Vanadium 2 positive is 3d3, right? Okay. Then you have chromium. Chromium is nothing but 4s1 3d5. Chromium 3 positive is 3d4, right? 3 positive is actually 3d3. Chromium 3 positive, 1, 2, 3. It is actually 3d3. Manganese 3 positive is, manganese is 4s2 3d5. Manganese 3 positive is what, everyone? Manganese 3 positive. 1, 2, 3, it will be 3d4, right? Chromium 2 positive, you take out 4s1 3d5. You take out 2 electrons, it will become 3d4, right? Manganese 2 positive is 3d5. Iron 3 positive is again 3d5 because iron is 4s2 3d6. You take out 3 electrons, it will become 3d5. Iron 2 positive is 3d6, right? Cobalt 2 positive and cobalt 3 positive. See, if you have cobalt 2 or cobalt 3 positive, cobalt 2 positive, cobalt is 4s2 3d7. So 2 positive is 3d7, 3 positive is 3d6. Both have the same color, right? Nickel is, I'll just delete all of them that are extra here. Okay? Nickel is 4s2 3d8. Nickel 2 positive is 3d8. Copper is 4s1 3d10. Copper 2 positive is 3d9. Can you see all of you? Can you see we have written the electronic configuration of all of them, right? Now we'll have to observe the colors here, right? So important things are that all the colors are very important, right? Like I'll just, should I write it somewhere, right, to make it easy for you, है ना? Let me just write it somewhere. Let's see the one that are in green category. Green category. Let's see the one they are in green category. What are the green category colors that they have asked? Vanadium 3 positive and nickel 2 positive. Vanadium 3 positive and nickel 2 positive is green in color. Others, iron 2 positive is green in color. See, when you make these kind of charts, it will be easy for you. So we have done green color 1, 2, 3. 3 colors we have done. Then let's talk about blue color. Blue color is quite repeated here, right? So let's talk about blue color. Blue color is given by which of the following? Blue color is given by, blue color is chromium. Firstly, it is vanadium 4 positive, chromium 2 positive, right? This we have done, this we have done, right? So after this, blue color is where? Blue color is copper 2 positive, that is quite famous. Okay? But this blue color question also they have asked. Green and blue they have asked already, right? From this table. If you're ignoring this table, that's your mistake. Then I would say violet color. Let's discuss violet color. Where is violet color? This one. Let's discuss violet color. Violet color. Violet color is given by vanadium 2 positive, chromium 3 positive, chromium 3 positive, then manganese 3 positive, then it is given by, wait a minute, vanadium this, then guys we have, oops, light has gone. Then guys we have, I think, only these 3, right, where violet color was given, right? Okay. Then what we have, let's discuss yellow color. Yellow color is given by, I'll just talk about, I have taken really not so yellow color. Yellow color is given by, because yellowish it will be difficult for you to see that it is yellow color, right? Yellow color is given by only Fe3 positive, that is also quite famous, right? So till now we have done yellow, green, blue, violet, we have done this, we have done this. We are left with the, now we are left with some individual colors. One is purple, then there is purple color. Purple is this one. Purple color is given by which? Purple color is given by titanium 3 positive, right? Then pink color is given by manganese. Pink color is given by manganese 2 positive. Then bluish pink color, right? Bluish pink color. Can we make bluish pink color? Let's try to do that. Bluish pink color. I think we won't be able to make that. So I'll just write bluish pink color, that is given by cobalt 3 positive and cobalt 2 positive. These are all the colors that you must remember. Okay? Yes, everybody, these are the colors that you must remember. See, in the form of table, it is very difficult to remember. But I think with this way, you can remember them easily. Right? With this particular way, you can remember them easily. green color, blue color, violet, they are maximum. Others are very 1 ions you have for that. Arey nahi, it's not a recorded class, beta. It's not a recorded class, right? Okay. Trick. I'll have to think about it, right? I'll see and think about the trick, and then I'll give you the trick, right? Okay. Then I'll think about the trick, that what is best way, then I'll make a short on this. Okay, then you will get to know about the trick as well. Okay, if I get a trick, then I'll make a short on that. Done, everybody? Tell me. Done? Let's see. Next is, okay, perfect. Then this was an important part from the colored compounds, right? The charts, right? The complementary colors, right? All these things. Now let's talk about formation of complex compounds, right? Let's talk about that. So complex compounds formation, let's talk about that. Now it's easy. Complex compounds are those in which we have seen coordination chemistry. We can see all these ions, all these coordination complexes had transition metals that were in it, right? Why so? Reason is that, what is the reason? Metal bind a number of anions, this giving complex with characteristics properties. Now why? The transition metal form large number of complex compounds. What is the reason? This is due to the comparatively smaller size of metal ions, high ionic charges and availability of d orbitals. That means they have very small size, right? This is due to comparatively smaller size of metal ions in this, right? High ionic charges are there, copper 3 positive, right? These kind of charges are there, cobalt 6 positive, right? High charges, oxidation state is high. The availability of d orbital, and when ligands are donating the electrons, these metals are able to accept the electrons, right? That is the reason. Okay, so simple. Then there is catalytic property. So now catalytic property, the examples are important here, right? The transition, the compounds, right? They are known for their catalytic activity. The activity is ascribed to the ability to adopt multiple oxidation state and to form complexes. Now, why there is this ability, right? This ability is there because to adopt multiple oxidation state and to form complexes, they are able to have the catalytic property here, right? Then we say that in case of vanadium 2, which is used in contact process, finally divided, it is used in Haber's. Nickel is used in catalytic hydrogenation are some of the examples, right? So let us mark the examples. Vanadium 5 in contact process, finally divided iron in Haber's process, nickel in catalytic hydrogenation, and even in the end of the chapter it is given, right? Catalyst at a solid surface into the. Now what is catalyst? Catalyst is basically, it will not itself get consumed in the reaction. It will first, what it will do, it will not itself get consumed in the reaction. No, it will not get consumed in the reaction. Simple thing is, a catalyst firstly will get reacted, it will get converted to some other oxidation state, then in the second step it will again come back to the same. That means, like this example that you have, Fe3 positive, that is getting converted to Fe2 positive. Then in the second step, Fe2 positive is again coming back to Fe3 positive. So iron is acting as a catalyst here. It is as it is even after the reaction, right? But it is helping the reaction to take at a faster rate. Okay. Catalysts at a solid surface involve the formation of bonds between reactant molecules and atoms and the surface of the catalyst, right? So basically catalysts on the surface of the metal, they react. So first row transition metals utilize 3d and 4s electrons for bonding. These metals, they utilize their 3d and 4s electrons for the bonding. This has the effect of increasing concentration of reactant at the reactant surface, also weakening the bonds in the reactant molecules. They will weaken the bonds, They will help. Now this is activation energy is lowered. That, see, thing is, if you have to do a reaction, this bond should break, only then reaction will take place. Catalyst help in breaking this bond, right? So that's how they lower the activation energy of that. This we have studied in apna chemical kinetics, we have studied this, right? Because of transition can change their oxidation state, they become more efficient as catalyst. For example, iron is used in a reaction of iron 3 positive, it's used to catalyze. This is an example that is given in your NCERT. That is why this example becomes important, that iron 3 positive catalyzes the reaction between iodide and persulfate ion, that is given over here, right? Then next is formation of the interstitial compounds, right? Now let's talk about formation of interstitial compounds. Interstitial compounds are those which are formed when small atoms like hydrogen, carbon, nitrogen are trapped inside the crystal lattice of metals, right? So interstitial compounds, you have voids in between the crystal lattice in which these small metals like these are trapped in the interstitial sites, right? And they are usually non-stoichiometric in nature, and they are neither typically ionic nor covalent. That means they are non-stoichiometric, not typically ionic or covalent. Like you have these, if you see this over here, they have like 0.56, 1.7, that is not, that is in fraction. So they are non-stoichiometric, right? The formulas do not of course correspond to any normal, wait a minute, the formulas normal, okay, because of the nature of, wait a minute, the formulas quoted do not of course correspond to any normal oxidation state. If you calculate the oxidation states here, these are not normal oxidation states that they will be in, right? So it will be fractional oxidation states. Because of the nature of their composition, these compounds are referred to as interstitial compounds, right? Right? They are called as interstitial compounds, right? They are called as interstitial compounds, right, everybody? The principal physical and chemical characteristics of these compounds are as follows. They have high melting point, that's why they are formed. They are very hard. Some borides approach diamond in the hardness. So that means boride is an example, right? Boride is an example of interstitial compound, right? But they are very hard, they have very high melting point, very hard, they retain metallic conductivity, conductance you can do here, right? And they are chemically inert, they don't react as such. So they can ask you statement based questions like, I'll just give you what kind of questions they can ask you. Which of the following is not true for interstitial compounds? These kind of questions they can ask you from here, not more than that. Like which of the following is not true, right? Assertion reasoning based, not assertion reasoning, mostly statement based question, which is statement 1 is true, statement 2 is true, or which of the following is not true. These kind of questions, okay? So an alloy is blend of metals prepared by mixing components. Let's now discuss about alloys, right? They also do alloy formation, like you mix so many transition metals and you make a metal, a new alloy out of it, which has the properties of all of them, right? So an alloy is blend of metals prepared by mixing components, right? Alloys may be homogeneous solid solutions. Now why they are homogeneous? They are homogeneous because we firstly melt it then mix it, so that they are mixed uniformly, right? In which atoms of one metal are distributed randomly among the atoms of others. Such alloys are formed by atoms with metallic radii that are within 15% of each other. They should have almost similar size, only then they can be formed. Right? Because of similar radii and other characteristics of transition metals, alloys are readily formed by metals. And in case of transition metals, they have similar radii, so they can easily be formed here. So you can say similar radii, alloys can readily be formed by these metals. Right? Then we will say the alloys so formed are hard. The alloys that you see here, right? The alloys that are getting formed are quite hard and have often high melting points. They have very high melting points. The best known are ferrous alloys. We have ferrous alloys, we have chromium, vanadium, tungsten, molybdenum, manganese, right? So these are our, because what they have is they are very hard and they have very high melting point. That's why they are formed. Like you have steel. Like, so now you will see that steel, stainless steels, all these alloys of non-transition elements such as brass, where metal and non-metal are there. Sorry, non-transition elements. So zinc is a non-transition element with a transition element. Bronze and bronze with copper and tin. Tin is a non-transition element, right? So that you must know what are the examples, right? Okay. Okay, everybody. Now this reaction students usually skip here. This is actually from the previous part. What do you mean by disproportionation of oxidation state? Give an example. You can give the example of copper as well. But here, because they have given you this example, I'll ask you to remember this one example here. And this we are going to do. Don't worry, this is a very, very important. This, my friends, is a very important reaction that you will see in KMNO4. Right? This reaction you will see in KMNO4. It's a very important reaction of KMNO4. Right? It's a very, very important reaction of KMNO4. In KMNO4 disproportionation, you will see this. Right? Okay? When we'll talk about KMNO4 and all. Right, everybody? Tell me. Now, are you ready to understand some important compounds of transition metals? These are KMNO4, K2Cr2O7, all these compounds. Are you ready for that? Yes, everybody. Ready to understand them? Ready to understand this? Okay. Ready everyone? Tell me. Because from 11th to 14th, I am on leave, so either I can complete your this chapter today, or I'll take class tomorrow, right? But tomorrow I already have so many batch classes as well. Yes, students, so let's do this, right, everyone? Let's do this, right? Okay. So firstly, let's see oxides and oxoanions of metals, right? So first is, these oxides are generally formed by reaction of metals with oxygen at high temperature. All the metals that you see except scandium form MO oxide, which are ionic. So this is important, that all the metals, what we say, all the metals except scandium form MO oxides, which are ionic. All will form MO oxides, which will be ionic in nature. Scandium will not form so. Highest oxidation number in the oxides coincide with the group number is attained in scandium to this. Now, if you see here, scandium is +3, right? the oxide of scandium, you have here +3 oxidation state. That means it is in group 3, right? This is +7. So oxide of manganese has oxidation state +7, and the group number of manganese is also +7. So this is what they are saying, they coincide with the group number. Beyond group 7, no higher oxides. Beyond, if you talk about beyond group 7, no higher oxides of iron like Fe2O3 are known, right? This we have already seen in oxides, okay? Beside the oxides, the oxocations, if you remember, we have done the same thing here. Before also we have done the same thing, okay? Wait a minute, where it was here. No, not here. Wait a minute. Array, this rough, I have to delete this, right? Looking so weird. Okay, we have seen it here. Can you see? Same thing we have done, right? So it is 2 times repeated in the chapter, right? These are your oxocations, right? Let's talk about other things here. As the oxidation number of metal increases, ionic character. Now this is important. Oxidation number of metal, if it increases, oxidation number of metal, ionic character decreases. In case of manganese, that's why we say manganese is covalent. This is very important. MnO2O7 is covalent green oil, right? Right? In case of manganese, this is covalent, but Cr and this are low melting points. If you see, this is very, very important, right? Manganese is in the higher oxidation state. We are saying that oxidation number, right, is inversely proportional to ionic character. That means it will be directly proportional to covalent character. That means it will be directly proportional to covalent character. So manganese here is existing in +7 oxidation state. That means its covalent character is going to be very high. That's why it has a covalent green oil, right? Okay. Now next is a very important point. Even CrO and V2O5 have low melting point, right? They have +5 plus wait a minute. They have +6 and +5 oxidation state. Okay, beta, it's just giving in a confusing manner, okay? This is +6 oxidation state. This is +5 oxidation state. So they are also like less ionic in nature. Because they are less ionic in nature, that's why they're, because ionic bond is stronger. If ionic character is less because of their high oxidation state, their ionic character is less, right? That is the reason they have low melting point. So you can also say oxidation number. If oxidation number is high, then melting point will also be low, right? And you can also say, right, I'm just giving it from your NCERT, right? Yes, you are too early for the class. In these higher oxides, acidic character is predominant. So higher oxides, if oxidation number is high, acidic character is also high. So these are the things that you must conclude from here. Okay? That you must conclude from here, that what is given to you and how you understand that. Okay, that you must conclude from here, right? Then we have Mn2O7 gives, now we are saying that Mn2O7 gives HMnO4 and CrO3 gives H2CrO4 and H2CrO7, right? Okay, so this is also important. This gives, like it takes, it replaces one manganese with hydrogen as well. Here in CrO3 also gives H2CrO4 and H2CrO7, right? So that is also important. Next is, this gives these two things, right? Vanadium is, however, amphoteric. Now, if you see here, the oxidation number is 7, that's why it is acidic in nature, and that's why it is giving HMnO4. Here it is plus 6, that is the reason it is giving H2CrO4 and H2C2O7, right? But in case of vanadium also it is existing in plus 5, but here there is another exception, that in this case, however, it is amphoteric. This is very important point, that V2O5 is amphoteric in nature. V2O5 is amphoteric in nature. It's a very, very important point. Though mainly acidic and it gives VO4, it is quite towards amphoteric. Mainly it is acidic. So it, though mainly acidic, means if you talk about the borderline, it is more towards acidic strength, less towards basic, right? But actually it's an amphoteric oxide. It is weakly acidic, you can say, right? So that's why it will give you, this is going to give you, though mainly acidic, right? It is going to give you V4O3 as well as VO negative salts. In vanadium, now this is very important and very, 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 asked question, right? That is regarding the basicity, right? Let's see that. Now in vanadium, the gradual change of basic strength from V2O3 to less basic V2O4, right? From the basic V2O3 to less basic this and to amphoteric this. Okay? That means, can we just write it, because based on this also they ask you the questions. Now if you see this here, V2O3 is more basic, then you have VO2, or you say V2O4, or you say VO2, then you have V2O5, right? This is basic, this is less basic, guys, please don't spam, right? Okay, don't spam, right? So V2O5 is amphoteric. Beta, don't do time pass here, okay? Okay, ji? Okay. So, beta, if NCERT is wrong, then I can't do anything, right? Okay, beta. If NCERT is wrong, then what I can do? Okay. Okay. So, what you have, V2O5 is less, that means you have basic is V2O3, then you have less basics V2O4, then you have amphoteric, right? Now see why it is so. Let's try to answer the oxidation states. Beta, can I just say, please, don't spam. I'll just block you like this, and there is no place for any kind of spammer here, right? Those students who wants to study, they don't study like this. Wait a minute. Chalo. Okay then, bye bye. Okay guys, let's see. Okay, I don't waste my energies or anyone's energy. I don't want to waste, right? See, let's see the oxidation state here. This is 2x minus 6 is equals to 0. That is x is equals to 6 by 2, that is 3. So here it is going to be plus 3, right? This is 2x minus 8 is going to be 0. So x is going to be plus 4, right? And here it is going to be plus 5. You can just directly say plus 3, plus 4, plus 5 as well. Now see one thing. More is the oxidation state, more is the acidic character. So that's why here acidic, that's why less is the oxidation state, less is the acidic character. That's why in this case what you will see, acidity increases as oxidation number increases. That's why from basic to less basic to amphoteric it is going, and beyond +5 you don't have any other oxidation state of vanadium, so purely acidic we don't have anything, right? Then guys, let's see, V2O4 dissolves in acid to give VO2 salts, right? V2O4, it will give VO2 salts. Let's underline this as well, right? Similarly, V2O5 reacts with alkali as well as acid, because V2O5 is amphoteric in nature. It reacts with alkalis, it gives you VO3 negative, and with acids, it gives you VO4 positive, respectively. This is with base. See, V2O4, we know that it is quite basic in nature. That's why it is reacting with acids. This is amphoteric, right? This is amphoteric. That's why it is reacting with base also. It is reacting with acid also. So with acid, it is giving VO4 positive. Well characterized, CRO is basic now. This is very, very important. Again, it is very important. CRO is basic in nature, right? And C2O3 is amphoteric in nature. Again, that is the same thing. Okay? These are very important things that they directly ask you in the exams. Which of the following is acidic in nature? Which of the following is basic in nature? So this is +2 oxidation state. This is +6 oxidation state. That's why lower oxidation state is basic, right? Okay. Thank you so much, Sunil. Thank you so much for your good words. Thank you, Vita. Okay, tell me. Clear, everyone? Right, we have done this as well. Then we have potassium dichromate. Let's study the compounds, right? Oxides and oxoions we have studied. Now let's study compounds like potassium dichromate, right? Potassium dichromate we have, potassium permanganate we have, right? We'll study all these things. After that, with the break, after that I'll give you break, then we'll start with F block elements, right? Okay. Sham, CH2 double bond CH2. You are asking me that. Why? Are we discussing organic chemistry here? Why suddenly CH2 double bond CH2 in vanadium titanium? Right? Arey beta, tell me. This is why the teachers are not, right, teaching you. The old team is not teaching you here. That is the only reason, right? You guys don't comment here, right? You don't clearly tell us that what you don't react. It's my second lecture after 3 months, and still I can see the kind of attitude that you guys have. Then can you see how much in depth I am teaching you? How much in depth I am teaching you? Can you see this over here? See the depth here, right? See the depth here of this one. And if you're still in your own zone that ma'am we don't want to reply, then guys, that is going to be my last lecture on Vedantu NEET English, right? Okay. Remember that always. I'm not giving you any dhamki or anything, right? But if I see you guys not reacting, not replying, I'll have to, go back. Because I already have a lot of batches. I'm already in batches. I'm already in Vedantu J English. So then I will not be entertaining you, right? You tell me you want to behave properly or not. I'll see you guys. When you guys reply, I'll start. Only two students, Sham and Shravas. What about others? Others are sleeping beauties. Hmm? Chalo, let's see. Potassium dichromate, right? That is K2Cr2O7, right? In case of, yes, K2Cr2O7, that is an oxidizing agent. We'll study two oxidizing agents, K2Cr2O7, right? Very good. Then, reply also, because otherwise my motivation goes, right? Then if you have K2Cr2O7, that is first, and then you have KMNO4, that is second, right? So if you talk about K2Cr2O7, that is Cr2O7 2 negative, that is called as chromate ion. Sorry, chromate I am saying. Dichromate ion. Dichromate ion. And there is another ion that you have, that is CrO4 2 negative, that is chromate ion. Okay, I'll just write this here. This you can paste it here. There are two things that you have here. One is chromate, other is dichromate, right? So I'll just draw the line also here, because that we have finished, right? Now see one thing, when I talk about chromate ion and dichromate ion, there some different things we have, but if the oxidation states, if I talk about, this is x minus 8 is equals to minus 2, that is plus 6. This is 2x minus 14 is equals to minus 2, that is 2x is equals to plus 2x is equals to 12, so x is equals to 6, right? So here also it is plus 6 oxidation state. So two things are same regarding chromate and dichromate. That is, one thing is same regarding chromate and dichromate, that their oxidation number is same, right? That is plus 6 plus 6. Now we'll see what are the other different things here. But before that, potassium dichromate is very important chemical used in leather industry as an oxidant for preparation of many azo compounds. When we prepare azo compounds, right, in the preparation of azo compounds, that is where nitrogen is there, they are used as an oxidants there, right? Dichromates are generally prepared from chromate. Chromate we have discussed, that is CrO4 2 negative, which in turn are obtained by fusion of chromite. So that means the starting material here is chromite. Now first important thing is chromite ore, that is FeCrO4. This is important, that is your chromite ore, right? They can directly ask you, yes. Right? So chromite ore, that we can say chromite ore is basically simple, that in case of chromite ore, that is the first thing that you will use here. From that you will prepare chromate. From chromate you will prepare dichromate. So that means the simple thing is that we have FeCr2O4. From this you will form CrO4 2 negative. From there you will form Cr2O7 2 negative. That is the all in all thing that we are doing, right? Okay. So with sodium or potassium carbonate in free access of air, the reaction with sodium carbonate occurs. So basically what we have here, how it is done. Firstly, from chromate we use sodium carbonate and we prepare chromate here, that is CrO4. The yellow solution of sodium chromate, that means chromate ion has which color? This is of yellow color. Chromate ion is of yellow color, right? That is filtered and acidified with sulfuric acid. Then this particular Na2CrO4, this is acidified with sulfuric acid, and you have the proportion of dichromate, that is Cr2O7 negative, right? That is a orange color solution. So we can say this is orange in color, right? Yellow to orange color we are shifting. Yes, very good guys. Janushri, Sham, very good, right? Okay. Okay, so this is what you should remember. Firstly, that firstly you have chromate from firstly you have chromita, or from there you have the preparation of yellow colored chromate. From chromate in acidified solution you have the formation of dichromate, that is of orange color. Okay, right everybody? Very good, very good. I can see your energy is very good. Happy to know that, right? Okay. What is next? Right, this we have done, right? Sodium dichromate is more soluble. Now we are saying that sodium dichromate, if you see, is more soluble than potassium dichromate, and that's why sodium to potassium dichromate is prepared. Right? So that is converted to potassium dichromate, simple. Right? Now that was not that important. I just told you what are important things that I told you. Chromite, this is chromite, to chromate, to dichromate. This is dichromate, bus, right? These are ions, that's it. This is what you have to remember. Now let's see, we know that dichromate is actually orange in color. So orange color crystals of dichromate crystallizes out. The chromates and dichromates are, now this line is very important, that chromates and dichromates are interconvertible. Very important line, that they are interconvertible in the aqueous solution depending upon pH. Very, very, very important line, right? How they are interconvertible depending upon the pH. Let's understand that, right? Let's see what exactly happens in the acidic solution, where pH, if you add acid there, where pH is less than 7, that means in the acidic solution, you will have the existence of dichromate, right? Dichromate will exist in acidic medium, right? And chromate will exist when the pH of the solution is greater than 7, that means in the basic medium, chromate will exist. Okay, so directly question can be asked, where dichromate is existing, where chromate is existing, right? Okay. I don't know why. I thought on Sunday students will be there because they'll be free from their classes, but I think Sunday students are enjoying, right? So pH you should remember, right? And whether it's dichromate or chromate, that you should remember, right? So for acidic medium, dichromate exists. From basic medium, chromate will exist, right? Then we have the structure. These two are very, very important things. This is very, very important. Okay. So dichromate only exists in, you can just say dichromate ion exists only in acidic medium. In basic medium, dichromate will not exist only. It means when pH is greater than 7, only then dichromate ion will exist. Otherwise, dichromate ion will not exist only. This is very, very important point, right? Then we have the structures. The structures of chromate and dichromate are shown below. Chromate ion is tetrahedral, dichromate ion consists of two tetrahedrals. Let's see how. This is chromate ion, CrO4, 2 negative. This structure is actually wrongly made here. This will be double bond O. This will be double bond. So they have not given it properly. It can also be formed as this. Cr double bond O, one is O negative, other is O negative. This way also you can write it, or you can also mention that all the sigma bonds you have mentioned. Now you are saying maybe partial double bond is existing in all of them. Because of resonance this will happen, right? And overall you have written the charge -2, or you can also draw it like this. So you can see it is a tetrahedral compound, and in case of chromate, just like, do you remember the case of Mn2O7? That was the same, two tetrahedrons were existing here. Listening to class, but they are 12th grade but vibing. They are in 12th grade but vibing. Great. That's nice, right? In 11th, if you are listening to the class and you're able to understand, that means you're already ahead of so many students out there, right? And you will not face difficulty in class 12. That's like for sure. You will be like, class 12 will go really smooth, right? So, Cr, here you have Cr2O7, 2 negative. So you can also prepare it like only two O negatives are there. You can also make it like this, and others are double bond, double bond, double bond. Because the one which is not neutral oxygen will not have negative charge. It will have a double bond, and the negative charge will not have a double bond, right? So either you can prepare it like that, or you can make sigma bonds everywhere and you can mention the charge here. But you can see there are first tetrahedral, and this is the second tetrahedral. So two tetrahedrons are existing here. So this is what they have written here, right? That in this case, in case of chromate ion, there is tetrahedral, and dichromate ion consists of two tetrahedrals with CRO bond angle of 126 degrees, right? Then if you see, then when you see, I am perfectly fine, Nandini, perfectly fine. Yes, Janushika, yes, very good. So, sodium and potassium dichromates are strong oxidizing agents. So, what we have seen, they oxidize, they themselves wants to get reduced, right? The sodium salt has greater solubility, that's why it is not used, and is extensively used in oxidizing agent in organic chemistry. It is used, but potassium dichromate, because it is not soluble, is primary standard in volumetric analysis, right? So you have two things. This difference is also, they can ask you, till now they have not asked this thing, but you should know that sodium salt is used in organic chemistry, right? And potassium dichromate is used in volumetric analysis, right? Okay, how you can remember this? Sodium is used in organic chemistry and potassium dichromate is used in volumetric analysis, right? Now we know that dichromate ion does not exist in acidic medium, does not exist in basic medium. Dichromate ion only exists in acidic medium, and that is the reason that dichromate ions will be converted to Cr3 positive here, right? Dichromate ions, if you see here, this is CrO4, this is your dichromate ion in the acidic medium. This will exist in the basic medium. Dichromate ion does not exist only. And in case of acidic medium, dichromate ion gets converted to Cr3 positive. That means dichromane itself, it is getting converted to +6 oxidation state. If you see this here, right, this is actually +6 oxidation state, and here it is +3 oxidation state. So it is getting reduced, and That's why how it is getting reduced, it is gaining 6 electrons here and it is getting reduced in the acidic medium. So first thing that you should remember, that it is a very good oxidizing agent because it easily gets reduced. Acidified potassium will oxidize. Now what are the things it will do? It will oxidize iodides to iodine, sulfides, wait a minute, you can say I negative to I2, S2 negative to S, right? Then tin 2 positive to tin 4 positive, right? Then iron 2 positive to iron 3 positive. It will oxidize all of them, right? It will oxidize all of them here. All of them will be oxidized here with the help of potassium dichromate. The full ionic equation may be obtained by adding the half reaction. You can add, let's say, from I negative to I2. It will lose 6 electrons because here 6 electrons are gained. You will add both of them, you will get the full overall reaction, right? Okay, this reaction, if you say, ma'am, let's talk about iron. Iron is getting, now this is about redox reaction. Okay, here redox reaction plays a very important line, right? Only NCERT session this is. What about concept questions completed, ma'am? Beta, that will be done, है ना? धीरे धीरे से will do everything, right? Okay, let's focus on what we are right now doing, right? So firstly, Cr to O72 negative, you should know that it is getting converted to this. Then if I say Fe2 positive to Fe3 positive, do you remember this you have done in redox reactions? Firstly, balance this equation, or you can just balance it by oxidation number method, reduction, oxidation half reaction method, right? These two you can balance this you will study in redox. So I will never advise any of the students to remember this full-fledged reaction. Beta, you don't have to remember. If you know, okay, if you know oxidation number method from redox reactions, Cr to O72 negative is converted to Cr3 positive. Just remember this much. Just remember this thing, and it itself, it is getting reduced, so it is oxidizing these all things. This is oxidizing all of them. Just remember this thing, right? And these are the electron gain, ma'am. In tin 6 electrons are gained. Beta, it's not like 6 electrons. Why 6 electron I am gaining here, losing here? Because here 6 electrons were being gained. That is the reason I have to make number of electron gain and lost equal. That's why it was done. Okay, so you don't have to remember full-fledged reactions here. Just remember this much. Ma'am, just concentrate on the concept, please. MVSAT results out, ma'am. How much rank should I get to get scholarship, ma'am? That to beta, I'll have to check about that, right? I have not gone through that, right? Which exactly rank you need to get. Rank you need to get among 2.5 lakh students, right? So, what are the marks? That depends upon which category you have given, NEET or J category, that depends upon that, right? Okay, so let's see KMNO4 now. Let's see KMNO4 now. So potassium permanganate, right? And beta, if you talk about inorganic chemistry, NCERT reading is most important here. That's why we are doing that. Okay? So potassium permanganate is prepared by, now what is the first thing from where it is prepared? It is prepared by the MnO2. It is prepared by MnO2 with alkali metal hydroxide. It is reacted with alkali metal hydroxide, oxidizing agent like KNO2. So MnO2 is reacted with like oxidizing agents like oxygen or KNO3, any oxidizing agent, and metal hydroxide. Then you have the formation of K2MnO4. So here also you have two things. First is MnO4 2 negative, right? Then there is MnO4 negative. MnO4 2 negative, this is X minus 8 is equals to minus 2. This is in plus 6 oxidation state. This is in plus 7 oxidation state. Here it is different. This is called as manganate ion. Manganate ion. This is known as permanganate ion. Permanganate ion. Permanganate ion. Okay, that is known as permanganate ion. Now one is manganate ion, other is permanganate ion, and the color also we'll talk about. Let's see this. Potassium permanganate is prepared by fusion of MnO2 with alkali this, and that's how you have the formation of manganate ion, that is MnO4 2 negative. Now this manganate ion, now to convert manganate to permanganate, you have so many different steps. First is just by reacting this manganate in the acidic conditions, it will be converted to permanganate, or commercially it is also prepared by firstly MnO2 to directly MnO4. MnO2 to manganate is same, that it is fused with KOH, oxidized with air or KNO2. The first step is same. Second is you have MnO4 2 negative to MnO4 negative. First is you directly directly you react this with this is actually very important, that directly K2MnO4 disproportionates in neutral or acidic medium to give manganate. That means this particular reaction is very important. This reaction is a very important reaction individually, that permanganate ion gives MnO2 and manganate ions give permanganate ion and MnO2. It's a very important reaction in itself, right? Oh, wait a minute, let me just do it again. Okay? It's a very important reaction in itself. Very important reaction, right? That MnO4 2 negative is converted to, that is manganate is converted to, right? Okay. Very good, Thoya. Awesome. Right? Okay, awesome. God bless you. Right? Now let's see. First is this question. This though you have to mark important, like most important reaction. Okay? Very, it has been repeated so many times, right? That manganate is converted to permanganate and MnO2, it disproportionates. How come it disproportionates? Because here it is plus 6 oxidation state, here it is plus 4 oxidation state, here it is plus 7 oxidation state. So whenever oxidation state is increased and decreased in the same reaction, that is called as disproportionation reaction, right? So now we are saying commercially how it is prepared. It is also prepared by electrolytic oxidation in the alkaline medium. Manganate is directly converted to permanganate, not that important, right? Then in the laboratory, manganese, in the laboratory how it is prepared? Mn2 positive is converted directly to manganate with the reaction with peroxodisulfate. Directly it is prepared. Okay, directly it is prepared, right? Till now they have not asked this, right? But you must know this, that Mn2 positive, right, with the peroxodisulfate, it is directly converted to, wait a minute, yes, okay. Now see, let's next one. Now this page is very important here, all the important things we are going to do here. Let's see. Potassium permanganate is actually dark purple, almost black crystals with isostructural with those of KClO4. Now this is also important, this question is also very important, that potassium permanganate is actually isostructural with KClO4, right? It has same structure as KClO4, that is also tetrahedral. Salt is not very soluble in water, but when heated it decomposes. Now this is also very important. Now these are the two reactions, decomposition reaction. Here we are saying permanganate. Can you see this? Here it is decomposition. It's not disproportionation, it's decomposition. This is also very important. This is also extremely important reaction that has been asked. Like so many times this particular reaction has been asked. Right? So many times this particular reaction has been asked. Like very, very, very important reaction. One is manganate is converted to permanganate ion. This reaction, manganate is converted to, wait a minute, manganate is converted to permanganate and MnO2, that is disproportionation reaction. This is decomposition where permanganate is giving you manganate and MnO2. Very, these two reactions are very confusing, and here O2 is also produced as a byproduct. So these two reactions are very, very important reactions. They ask you from MnO, they ask you from KMnO4. Right? Then two physical properties, it's intense color and it's diamagnetic. It is diamagnetic in nature. Can you tell me why? Because Mn plus 7 is actually D0, right? So that's why 3D0, so that's why it is diamagnetic in nature. With temperature dependent weak paramagnetism, if temperature, it is also dependent on the temperature. If temperature is there, then the electrons can split. Right? These are explained by use of molecular orbital theory, which is beyond present scope. We are not going to study it here, right? So remember that your manganate is actually green in color. So I'll just write it here. Manganate is green in color and permanganate is violet, or you can say purple blackish in color, right? Dark purple in color. So if you see their structures, they are tetrahedral. In manganate you have only one O negative. You can see this over here, you have only one O negative. Here you have two O negatives. No. In case of permanganate you have only one O negative. In case of manganate you have two O negatives, because what is manganate? Manganate is MnO4 2 negative. Permanganate is MnO4 negative. Okay. Now next is manganate and permanganate ions are tetrahedral. Pi bond take place with, now this is which kind of bonding? Which kind of pi bonds? This is p pi d pi bonding, right? Why? Because this is between p orbitals of oxygen and d orbitals of manganese. So that's why it is a p pi d pi bonding with p orbitals of oxygen and d orbitals of manganese, right? Green color is paramagnetic. Now we know that in this case you have Mn plus 6, that is nothing but 3D1. So that is why it is paramagnetic in nature, right? So you can also write this here. This is actually 3D1, this is 3D0. That's why this is diamagnetic. This will be paramagnetic because it has unpaired electrons, right? Then let's talk about two things, that acidified permanganate and non-acidified, that means basic or neutral, how it gives different compounds. So acidified, if you talk about acidified permanganate solution, that will oxalate to carbon dioxide, Fe2 positive. Now this question also has been asked, that it converts oxalate to carbon dioxide, Fe2 positive to Fe3 positive, NO to NO3 negative, I negative to I2. Now the last one is differentiating, that's why I am marking it here, right? Otherwise all are important here, right? And remember this thing here, I'll just make it easy for you, that in case of acidic medium this happens. In case of acidic medium, MnO4 negative is converted to Mn2 positive. In case of basic or neutral medium, this will take place, it is converted to Mn2 positive. Now this is also important that permanganate in case of acidic and basic medium, that will give you different answers. In case of basic it is MnO2, in case of acidic it is Mn2 positive, right? In this case, if you see, this is very low, this reaction is very slow. This particular reaction that you have, that is from MnO4 negative to MnO4 2 negative, this reaction you will not see because this is very slow. Okay, yes beta, we will give you the break. So the full reaction will be written by adding these. If we represent the reduction of permanganate ion, right, to manganate, then these three cases are possible. Out of this, only these two are real. Others are only this one and this one will be possible. This particular reaction here will be so slow because its electrode potential is very less. Here electrode potential are high, that's where this is going to be there. But in basic medium it's different, in acidic medium it's different. We can now, this is the same thing, although many reactions can be understood by considering redox potential. Permanganate should oxidize water, but in practice reaction is extremely slow. So we are saying permanganate should be converted to this one, but its reaction is extremely slow, right? So to make this particular reaction happen, you should have Mn2 positive ions are present or temperature should be raised. Now this is a very important point, that is permanganate at when H positive concentration is 1, because here H positive concentration is 1. If you see here, we can say H positive concentration is 1, right? So that means this line we are talking about here, right? That H positive concentration is very less here. So it should oxidize water, but in practice the reaction is extremely slow unless manganese 2 positive ions are present or the temperature is 8. Otherwise this reaction is very slow to occur. That's why we will only see in acidic medium. Firstly, in acidic medium, what we will say, MnO4 negative to Mn2 positive will be the reaction, right? Other is, it will convert I negative to I2. It will convert Fe2 positive to Fe3 positive. It will convert oxalate to carbon dioxide, sulfide to sulfur, SO3 2 negative to SO4 2 negative, NO2 negative to NO3 negative. Okay, that's all. You don't have to learn the balancing reactions that we have done in redox. Just remember, in acidic medium, this is converted to Mn2 positive, and what are the oxidations that it is doing. In neutral medium, we know that MnO4 negative is converted to MnO2, right? Then it is converting I negative to iodate. This is very important. This is very important, that here in this medium it is converting I negative to I2, right? I negative to I2 in acidic medium. In case of basic medium, this is converted to iodate. In case of basic medium, it is converted to iodate, right? That we have done already. Rasi, you need to see the lecture before. I have done it 2 hours before. Right here, SO3 2 negative is SO2O3 2 negative is converted to SO4 2 negative, and Mn2 positive is yes. Okay. Then we also say the thing that we talked about here. If you remember, we said that manganese 2 positive ions are needed to convert MnO4 negative to MnO4 2 negative. So to convert MnO4 negative, when you have manganese ions, then it is converted to MnO2. Okay? This reaction is also important, because this is quite confusing reactions. These are confusing reactions. So This is also individually important. Manganese salt is oxidized to MnO2 in the presence of zinc sulfate or zinc oxide catalyzes. This is important. Okay, right everybody? Then permanganate titration presence of HCl are unsatisfactory since HCl is oxidized to chlorine. Now this is important, that permanganate titrations, if you remember, in case of titration we don't use HCl. Why? Because in presence of HCl, hydrochloric are unsatisfactory since HCl are oxidized to chlorine, right? This is also important, that why permanganate titrations in presence of HCl are unsatisfactory, because HCl is converted to Cl2. That's why we don't use HCl. Now next is, besides any use of analytical chemistry, potassium is also used favorite oxidant in organic chemistry. It is used in bleaching, cotton, silk, other textile fibers, and decolorization of oils are also dependent on strong oxidizing power of the potassium permanganate. Right everybody? Okay. So we have done D block elements. Now very small part, that is your F block elements we are left with, right? Okay, very small part, that is F block elements we are left with. That I'll do after the class, right? Okay, chalo. So what I'll do now after the class, I'm saying after the break we'll do that. Right now, before starting F block elements, I'm gonna give you a break of how much time? Tell me. I'm gonna give you break of 20 minutes. So I'll see you all at 4 p.m. Okay. So the class is going to resume at 4 p.m. because this is also lunch time. So let's have our lunch and I'll see you all at 4 p.m. and then we will end the class. Because after that, a little bit is left, only 1 hour session is left, that we'll do after the class, after lunch time, right? Okay, then I'll see you all after the break at 4 p.m. So, hi everyone. So, I am back. Yes, students, do let me know if I am clearly visible and audible to all of you so that we can start with the session. Let's see, let's start with the session that we were doing. So, till now we have completed D block. Now we will be doing F block elements. Let's start with that. Right, everybody? I think one more hour and the chapter will be completed. Right? Okay? Just one more hour and the chapter will be completed. Right? So, the F block consists of two series. One is, we are saying, one is lanthanoids and other is actinoids, right? So, that way I told you in the starting of the chapter that what are lanthanoids, that are, and actinoids, they are inner transition elements. And both in lanthanoids and actinoids, you have 14 elements. Now, if you see, lanthanum is a part of, it's like this. This is your D block. This is 3D, 4D, 5D. Here you have, wait a minute. This is D block, right? This is 1, 2, 3, right? So, this is your lanthanum. Array yaar. Let me just, okay. This is D block, this is 3D, 4D, and this is 5D, this is 6D. First element here is lanthanum, here it is actinium. So after lanthanum you have 4F series, after actinium you have 5F series. This lanthanum series is called as lanthanoid, this actinium series is called as actinoids, right? So these are in the F block elements. Now, lanthanum closely resembles lanthanoids. That is why we study there in lanthanoids only, for which great general symbol of Ln is often used. Similarly, a discussion of actinoids include actinium besides 14 elements. Lanthanoids resemble one another closely, then do members of ordinary transition elements in any series. So they resemble each other so much. Why? They have only one stable configuration and their chemistry provides an excellent opportunity to examine the effect of small changes in size and nuclear charge along with otherwise similar elements. So basically in lanthanoids we are going to study electronic configuration. Other things are not important here, right? Because one thing is important, that their lanthanoids resemble one each other a lot, right? They resemble each other closely, right? Then other elements, then other series, if you talk about, they have only one oxidation state, only one stable oxidation state is there, and that oxidation state is +3 oxidation state is stable for lanthanoids. Right, the chemistry of the actinoids is on the other hand much more complicated. That's why actinoids, so you will not study only. The complication arises partly owing to the occurrence of wide range of oxidation state. Firstly, in actinoids you have a wide range of oxidation states and their radioactivity also. That's why we don't study it here. Two series will be considered separately here. So firstly, let's understand lanthanoids. Name, symbols, electronic configuration, all the things we'll study about lanthanum and lanthanoids here, as you can see. First is the electronic configuration, from where the questions are asked. So we know that here the electronic configuration 6s first you will use, then you will use 4f orbitals, right? In 4f you will fill the electrons from 1 to 14. So firstly, let's see the electronic configuration from this table. Now in lanthanoids, this table is most important table from where questions are asked. If you want to skip other things, you can skip, but this table you cannot skip, right? This table is very, very important for you. So you cannot skip this table. Other things you can skip, right? Other things you can definitely skip. So first is that you should know that in case of lanthanum, right, in the electronic configurations of lanthanum, in case of cerium, 5D is there in lanthanum, cerium, gadolinium and lutetium. Okay. 5d1 is there in lanthanum, cerium, gadolinium and lutetium. This is important. 6s2 is there in all of them. Okay, I'm just telling you how to learn the electronic configuration here, right? Firstly, remember that 5d1 is there in some specific elements, 6s2 is there in all the elements. Then how it will start from cerium. Then if you see this, from cerium it starts with cerium to lutetium, it starts with, here if you can see, this is 1, 2 is skipped, then 3, 4, 5, 6, then 7, 7, then 8 is skipped, then 9, 10, 11, 12, 13, then 14, 14. Okay, so you will write it like that. So you will write it 1, 2 is skipped, 3, 4, 5, 6, 7, 7, then 8 is skipped, then 9, 10, 11, 12, 13, 14, 14. So if you see, these are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 14. Okay? So all these are filling of 4f orbitals from cerium to lutetium. All these are the filling of 4f orbitals from cerium to lutetium. This is a way of learning the electronic configurations here. Then the electronic configurations that are important here, let's talk about that. The electronic configurations that are important for you. Let's see that. See, we'll see where you have 0, 7 or 14. Okay, like this is 0, this is 0, right? This is 7, this is 7, then this is 7, then this is 14, this is 14. So you must remember these electronic configuration that I'm going to write here, right? So you must remember these electronic configurations. First thing is lanthanum 3 positive. Lanthanum 3 positive. I'll tell you where 4f0 is there. Cerium 4 positive. Lanthanum 3 positive, cerium 4 positive, you have 4f0 here, right? Then europium 2 positive, gadolinium 3 positive and terbium 4 positive, right? If you can see, this is terbium 4 positive, okay? And in terbium 4 positive, you have 4f7, right? Then ytterbium 2 positive and lutetium 3 positive. Ytterbium 2 positive and then you have lutetium 3 positive. Okay, understood? Tell me. So these are the values that you must remember, right? These are the values that you must remember. Wait a minute. Okay, that where you have 4f0, where you have 4f7, where you have 4f14, these things you must remember, right? This is from this table that is important for you, right? Now we'll understand in the theory part what is written. Now it will be quite simple for you. Achha, firstly I'll teach you oxidation state, then I'll teach you radius. Oxidation state is lanthanum 2 positive, these are predominant species, right? Lanthanum 2 positive and lanthanum 2 positive, if you see, lanthanum, wait a minute, array nahi, we are saying that lanthanum 3 positive, that means in common oxidation state is, now see this thing, I'll make it even simple for you. Common oxidation state we are saying is +3. Okay, this is common oxidation state. But it also exists in +2, +4 oxidation state. As you can see, like cerium you have here, that is existing in +4, gadolinium so existing in +3 only, terbium is in +4, ytterbium is in +2, europium is in +2. So these are the oxidation states that are not +3, and that is the reason the irregularity arises mainly from extra stability of empty, half-filled and fully filled orbitals. Now because if you can see F0, this is F7, this is F14, that is why these cerium 4 positive, europium 2 positive, why these are existing? Why cerium 4 positive, europium 2 positive, ytterbium, terbium 4 positive, why they are existing? Because of extra stability. Now we are saying that, very important line, cerium 4 positive, right? Cerium 4 positive is a strong oxidant. Why? Because cerium, if you see cerium here, cerium 4 positive would want to, because the common oxidation state of cerium is cerium 4 positive, or you have terbium 4 positive. They both will be converted to +3. That's why they want to decrease their oxidation number. So they would want to get reduced. That's why they are very good oxidizing agents, right? But if you talk about europium 2 positive and ytterbium 2 positive, they will increase the oxidation number. Here oxidation number decreases, here oxidation number increases. That's why they want to get oxidized, and that's why they will be behaving as very good reducing agents, right? Okay. So that's why we say cerium 4 positive is actually possible. 4 positive to 3 positive is by electrode potential also you can say this is positive. That means this particular reduction is possible. That's why it's a very good oxidizing agent, right? However, reaction rate is very slow, and hence cerium is a good analytical reagent. PR, NB, TB, DY also exists. Now this is an important factor. This is also, they have asked you in PYQs that PR, ND, TB, DY, they also exist in +4 oxidation state, but only in the form of oxides, that is MO2, right? This is a very, very important line, that all these will also exist. Out of this terbium, you know why it is existing, because of stable configuration. Dy, PR, Nd, they don't have stable configuration, still they exist in +4 oxidation state, but only in the form of oxides like MO. Very, very important line, right? Then europium, if you see 2 positive, is a strong reducing agent, that we have already talked about that why, right? Ytterbium, we also say ytterbium is also a reductant, that I have already written here, that ytterbium is also a reducing agent. This is an oxidizing agent that I have already written here, right? Terbium 4 positive have half filled, and that's why terbium 4 positive is an oxidant, that means oxidizing agent, that I have written here, right? That cerium and this I have written on the sidelines, right? So that's why I am not highlighting it here. Okay, these I am not highlighting here. Things that I have not written there, I am highlighting that okay, all these are existing, but PR, ND, TB, DY, they all are existing as +4 oxidation state, which is a very, very, very important line. Okay. Similarly, YB positive have this, we have discussed, guys, right? Chalo. Now let's see this. Okay, now this is important. This is also different, that the behavior of samarium is very much like europium, exhibiting both +2 and +3 oxidation state. Now, why is samarium? If you see, Samarium is having both +2 and +3 oxidation state. That is also a different behavior of samarium. It is not related to its stable electronic configuration. It is just existing in +2 also. It is behaving like europium only. So the one that we have discussed from electronic configuration, that I have written here, right, that I am marking in the table. Then why, which one is oxidizing reducing agent, that I have written in these two things. Then guys, the two lines that I have highlighted here, this line is a very important exception, and this line is also very important exception, that samarium, out of nowhere, it is existing in +2 and +3 both. Okay, understood? Then let's talk about the atomic radii. Now I have told you about lanthanoid contraction also, that in case of lanthanoids, after lanthanum, you start filling 4f orbital, right? You start filling 4f orbital also. So what will happen? 4f has poor shielding effect. Poor shielding effect. Because of its poor shielding effect, what will happen? If I say this is nucleus, these are 4f electrons, and this is the outermost electron. The outermost electron gets attracted because the 4f orbital is not shielding it properly. That is called lanthanoid contraction. That is the reason 4d and 5d series have almost same radii. Okay? So we say that is because of lanthanoid. So lanthanoid contraction is a unique feature, right, which has various consequences, right? Is a unique feature in chemistry. It has reaching consequences in the chemistry. Third transition of the elements. The decrease in atomic radii is not regular. Now, if we say that when we see the decrease in the atomic radii is not regular as it is regular in M3 positive ion. So that's why here we have written M3 positive ion. Okay? So they will only ask you one thing, not about metals, but M3 positive. M3 positive, it is regular, right? This contraction is of course similar to observed in an ordinary transition series and is attributed to same cause. The imperfect shielding of one electron by another in the same subshell. Now what is happening, because 4f orbital is having a very poor shielding effect. That's why it is not able to show. You fill one electron, then second, then third. What will happen? Because of its poor shielding effect. See, when you're adding electron, you're also adding proton. So here you're adding proton, charge is increasing, and here you have electron. Electron is also increasing. But this has, if I say this is proton and this is electron, this electron and this proton also you are adding. Nuclear charge is increasing with increase in atomic number, and electrons are also increasing here. But the problem is that electrons are increasing in 4f orbital, which is poor shielding effect. That's why overall the size is decreasing, right? Because nuclear charge is increasing because of proton. Electrons are also increasing, but electrons are increasing in 4f orbital, which has poor shielding effect. There is no benefit of that, right? This contraction is of course similar to that of observed in ordinary transition series and is attributed to the same cause, imperfect shielding. Okay? The shielding of 4f electron by another is less than 1d electron by another. Now we say d electrons are still having better shielding if it as compared to 4f electrons, right? There is fairly regular decrease in the sizes with increasing atomic number. So the cumulative effect of contraction of lanthanoid series is known as lanthanoid contraction, cause the radii of members of third transition elements to be very similar to that of. Now there is a cause of that. Now this we have studied in D block as well. Because of lanthanoid contraction, two things are happening. Third transition series very similar to second transition series. Okay. The third transition to be very similar to second transition series. That means third transition means 5D and this means 4D. So the radius of 4D and 5D series becomes equal. That is written here. Okay. The almost identical radii of zirconium and hafnium is the consequence of that one. Right? Okay. Yes, that's it. Okay, everybody. Chalo, let's now understand. Yes. Now you will see one thing from this table, right? That samarium and europium 2 positive, they have very good radii. Their radii is very large. Okay, this is shown here. Exceptionally, it is even more than lanthanum. Right? That is important. This question also they can ask you. Samarium and europium, large radii. And out of this also, samarium is more than as compared to europium. Okay? Right, everybody? Understood? Chalo. Now I think that is done. Now let's see other things here. Like very important things I'll tell you here. Non-important things we are not going to see. Okay, because right now the important things I have told you, electronic configuration, this chart is very, very important, and these two things that I have told you over here, this page is very important. After that, let's see. Now all the lanthanoids are silvery white solids of soft metals. Let's underline the important points here. Okay. Silvery white soft metals and tarnish rapidly. Hardness increases with increasing atomic number. Samarium, now this is important. Samarium being steel hard. Samarium is very, very hard, right? Then the melting points range between this to this, but samarium melts at 162K. Melting point are usually below 1200 Kelvin, but samarium has exceptionally high melting point also, right? Then we are saying they have typical metallic structure and are good conductor of heat and electricity. Density and other properties change smoothly, except for density and other properties change smoothly except for europium and terbium, occasionally for samarium and terbium, right? Okay, so density and other properties, they will change smoothly for Europe, but for europium and terbium they will not change at all, and they will change occasionally for samarium and terbium, right? Then you have trivalent lanthanoid ions are colored both in solid state. Now just like DD transitions, you have FF transitions here, right? May be attributed to presence of F electrons. Now here we know that lanthanum 3 and lutetium 4, lanthanum 3 positive, lutetium 3 positive. If you see, lutetium 3 positive is 4F14, lanthanum 3 is 4F0. So always remember, these are colorless. Lanthanum 3 positive, cerium 4 positive, ytterbium 2 positive, lutetium 3 positive, they are all colorless. Why? Because they have zero or fully filled electronic configuration. Okay? Absorption bands are narrow. Neither this show any color, rest do. Yes, absorption bands are narrow, probably because of excitation within F level. So F level, the excitation is within the F level, so absorption band are not very broad, they are very narrow. Lanthanoid ions other than F0 type like La3 positive, this and this are all paramagnetic. That means, guys, we know that these are diamagnetic because they have no unpaired electron. These are diamagnetic. Except others are, you can say, others are para because they will always have unpaired electrons. Others are paramagnetic except for F0 and F11, right? So this is an important line to remember. This particular and this particular are all paramagnetic. Lanthanoids ion other than these are all paramagnetic in nature, right? Then first ionization enthalpy of lanthanoids are around 1600 kilojoules. Second is very high comparably with those of calcium, very high. A detailed discussion of variation of third ionization enthalpy indicates the exchange enthalpy considerations appear to impart a certain degree of stability to the empty, half-filled and completely filled f orbital. Now third transition, 3 positive, that depends upon whether you are getting into a stable or unstable electronic configuration. This is indicated from abnormally low value of third ionization enthalpy of lanthanum and gadolinium and lutetium. Now can you tell me why they have low value? Third ionization enthalpy depends upon whether you have F0, F7 or F14. So in case of lanthanum, gadolinium and lutetium, we know that in the +3 state, they are all, this is F0, this is F7, this is F14. So they are all in the stable electronic configuration. That is why they have very low value of third ionization enthalpy, right? Chemical behavior in general, early members quite reactive. The early members of the series are quite reactive to calcium, but increasing atomic number, they behave more like aluminium. Now this is also important that earlier members of the series are similar to calcium, but with increasing atomic number, they behave like aluminium, right? Okay. So mostly they exist in +2 oxidation state. So you will see here, whenever they do reactions here, mostly they will exist in +3 oxidation state, right? Mostly they will exist in +3 oxidation state, Ln2O3. With acids they give H2, with halogens they give LnX3, with hydroxide they give LnOH thrice, here they give LnC2, Ln Ln twice S3, right? So values of E0 of half reaction, values of E0 for half reaction are in the range of -2 to this, except for europium, for which the value is this, right? Usually values are -2.2 to 2.4, but for europium the value is even lower. That means this is of course a small variation. The metals combine with hydrogen when gently, now this is all about, they are telling about the reactions in the gas. The carbides, they form this and these kind of carbides. They liberate hydrogen with dilute acids, burn in halogens to form halides. They form metal oxides as well. They form hydroxides as well, right? A definite compounds, not just hydrated oxides. They are basic like alkaline earth metal oxides and hydroxides. And this important term is that they are basic, right? Wait, that they are basic in nature. Their oxides and hydroxides are basic in nature, right? So this you must remember, this you must remember, these carbides you must remember, right? Then this is, next is, the best single use of lanthanoids is the production of alloys. And here one very important alloy is mish metal, right? One very important alloy is mish metal. Now it consists of 95% of lanthanoid metal, iron is 5%, traces of all these non-metals and metals are there, right? So a good deal of mish metal is used in magnesium based alloy to produce bullets, shells and lighter flint. Then mixed oxides of lanthanoids are employed as catalyst in petroleum cracking. Some individual lanthanoid oxides are used in phosphorus in television screen and similar fluorescent surfaces, right? So mish metal, you must know what is mish metal, right? And all these things, you have to go through yourself as well. As such, the question is not asked from here. Question is asked only from electronic configuration and these things that I am telling you here, right? The important things I am already underlining, and you will see very rarely, very rare highlighter, you will see very rare it is there. Highlighter maximum was in D block, right? So regarding actinoids, right? You don't have to remember all like electronic configuration as like fully you should remember that, I am not saying, but you must remember thorium 4 positive, because that is thorium 4 positive is 5F0. Then you must remember curium 3 positive, that is 5F7. Berkelium 5F7, which is 5F7, berkelium 4 positive. Then you must remember lawrencium this, okay? So you can write it here, 4F0 is in actinium 3 positive, right? And it is there in thorium 4 positive, right? F7 is there in curium 3 positive. Only this much you should know. Berkelium 4 positive, that's it. Then 4F14 is there only in lawrencium 2 positive, sorry 3 positive, right? Only this much you need to know, rest of the things you don't need to know, okay? Only this much, if you remember, that is more than enough for you, right? Only this much is more than enough for you, right? Then actinoids are radioactive elements, you must remember they are that's why the studies are very less. Radioactive elements, and the earlier metals have relatively long lives, the later ones have very, like one have half-life value ranging from a day to 3 minutes for lawrencium. The latter members could be prepared only in nanogram quantities, very small. These facts render their studies. That's why the questions are also not asked from here, right? Their electronic configuration, I told you that as such you don't have to remember. Just remember 7s, 5f and 6d are filled here. 14 elements are formally added to 5f, though not in thorium. But from Pa onwards, 5f orbitals are complete at 1. That means what we are saying, if you see the electronic configuration, in thorium we are not filling 5f orbital. Can you see that? This is very important. In thorium, which is an element of f orbital, here you don't have filling of f orbital. This is very important. This configuration they can ask you. This configuration. Rest of it, all of them have 5f orbitals filled. But only in case of thorium, thorium is the only element which belongs to f orbitals or f orbital, and still it does not have any f orbital filling here, right? Okay. Yes, everybody? Tell me, right? So, what we are saying here, the 14 electrons are added in this, though not in thorium. Thorium it is not added. In 5f, thorium is not added in that, but from Pa till the end it is added. The irregularities in the electronic configurations of the actinoids, like those of lanthanoids, are basically, we know that there are some stable electronic configurations, like you have 5F0, F this and this. But firstly, let me just highlight this one. You should not forget this thing, right? This, so you know that they are stable. Now, this also I have told you, the configuration of AM and CM are this and this, right? So, when we are saying related to the stability of F0, F7, F14 occupancies of 5f orbital, thus the configuration of AM and CM. That means here it is 5f7, here also it is 5f7, as you can see, right? Without any oxidation state, it is 5f7 here, right? And it is 5f14 in case of nobelium and lawrencium, right? So these are also like rare chances of asking, but these are important, right? Okay, so I'm not asking you to learn all of them, but some you should. Now again, just like actinoid contraction, you have just like lanthanoid contraction, you have actinoid contraction because of poor shielding effect of 5f electrons. And remember that actinoid contraction is even stronger than lanthanoid. Actinoid contraction is stronger than lanthanoids because 5f orbitals are even poor shielding effect as compared to 4f. That's why contraction in actinoid is much more greater, right? Then if you talk about the oxidation state, they show variable oxidation state. Their general oxidation state is +3, but otherwise the elements if you see, the elements in the first half of the series frequently exhibit higher oxidation state. Maximum oxidation state increases from +4 in thorium to +5, +6, +7 in PaU, NP, but decreases in succeeding elements. The actinoids, remember the lanthanoids in having more compounds in +3 oxidation state than in +4. So here also common oxidation state is +3. +3 and +4 ions tend to hydrolyze because of the distribution of oxidation state among the actinides is so uneven, so different from the former that later elements, and it is unsatisfactory to review the chemistry in terms of oxidation state. So that is also not studied. So basically they are saying that what you have seen, that earlier it is increasing higher oxidation state, then for NP and PU it is maximum, then again it is decreasing. But there are so many oxidation state that it is very and it's not possible for us to understand that completely, right? Then comparisons we have, the actinoids metals are silvery in appearance, display variety. The structure variability is obtained due to irregularities in metallic radii, which are far greater than in lanthanoids, right? That's why the structure's variability is there. Actinoids are highly reactive metals, especially when finally divided. Gives a mixture of oxide, hydride, that means they are very reactive. Hydrochloric acid attacks all the metals, but most are slightly affected by nitric acid owing to the formation of protectin. Now this is important, right? That hydrochloric acids attacks all the metals of actinoids, but nitric acid, they will form a protective layer, right, of oxide, which will not let them react. Magnetic properties, if you say, magnetic properties of actinoids are complex than those of lanthanoids. Although the variation in the magnetic susceptibility, actinoid number of this electron is a free para to corresponding, the latter have higher values. So this is also not important for you. Then it is evident. Now I think this was the last page only what we are studying here, right? Like not that much important things are there. I'm just will complete. Yes, yeah, we will complete it today, right? I'm just trying to figure out what are the important lines from here. It is evident from the behavior of the actinoids that ionization enthalpy of early actinoids are not accurately known but are lower than that of early lanthanoid. Now this is also a very important line, that let me just write it. This is important line. Ionization enthalpies of early actinoids are lower than lanthanoids. They are not accurately known, but they are lower. That is important. This is quite reasonable since it is to be expected that 5f orbitals are beginning to be occupied. They will penetrate less into the inner core. See, this is important line, right? This one is important, that if you see 5f orbitals, this is 4f and this is 5f. So 5f electrons, 5f orbital is more towards the outer side as compared to 4f. So that's why 4f orbitals are near to nucleus, 5f orbitals are not near to nucleus. That's why 5f orbital, it is easy to lose the electron, right? Penetration in the inner core is more. That's why 5f electrons will be more effectively shielded from the nuclear charge than 4f electrons, right? So 5f electrons don't have that much contact with the nucleus. That's why outer electrons are less firmly held and they are available for bonding in the actinoids. That's why actinoids are very highly reactive, right? Then different characteristics we have discussed reveal that behavior is similar to that of lanthanoids is not evident until the second half of the actinoid series, right? So we are saying that a comparison of actinoids and lanthanoids with respect to general characteristics reveals that behavior similar to that of lanthanoid is not evident. That means they are not that similar, right? However, even the early actinoids resemble the lactanoids, showing close similarities with each other and gradual variation properties which do not entail change in oxidation state. So we can say early actinoids resemble, but later on the resemblance decreases, right? The lanthanoids and actinoids have extended effects on the sizes. Lanthanoid contraction is more important because of we study it in D block as well, so that's why it is more important for you, right? So some important applications here. Now, based on this applications, this is DNF block application here. Match the following kind of question can be asked. Match the following question can be asked here. Okay? So, we have iron and steel are most important construction material. Here you will see a lot of lines here that are important. They are construction materials, right? So firstly, I'll just write it construction materials. The production is based in the reduction of iron oxides, removal of impurities, addition of carbon, alloying materials such as chromium, this and this. Right, so here iron and steel are most important. Their production is based on reduction of this, right? Some compounds are manufactured for special purposes such as TiO for pigment industry, right? Then Mn2O for use in dry battery cells. This, if you remember, we have done in electrochemistry, dry battery cells it is used. The battery industry also requires zinc and nickel cadmium. That is also required. Elements of group 11 still are worthy to be called as coinage metals, right? Because coins are, although silver and gold are restricted to the collection items and our contemporary UK copper coins are copper coated steel. Copper, that means inner it is steel, outer is copper coated it is. Silver UK coins are copper nickel alloy, right? Copper and nickel alloy. So these are all the uses. Many of the metals and their compounds are essential catalysts. Now this is very important. V2O5 is used in oxidation of O2 in the manufacture of oxidation, that is contact process. This is nothing but this is contact process. Contact process. Okay? Then there is TiCl4 and this are the bases of Ziegler-Natta catalyst used for manufacture of polythene. Then next is iron catalyzes Haber's process for production of ammonia from this. Then nickel catalyzes hydrogenation of fats to proceed, right? Then Wacker process, the oxidation of ethine to ethanol is catalyzed by PDCl2. These are all important questions that they have asked, right? Then you have nickel complexes are used in polymerization of alkynes. Organic compounds such as benzene, है ना? Polymerization of alkynes and organic compounds such as benzene. Then we have photographic industry. Photographic industry relies on special light sensitive properties of AGBR. So this full paragraph here is very, 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 very important, right? Because direct questions are asked based on which catalyst is used where, right? Okay. So that's it. We have done it, guys. You can go and do the summary, watch the summary for this one, and that's it. Tell me, everyone, if everything is clear to you or not. Is there any problem in what we have discussed? Right? Yes, students. Yes, everybody. So finally, it's been almost 5 hours, right? And we have completed the class. Yes, tell me, everyone. Now I'll be giving you the PDF on our Telegram channel, on my Telegram channel, that is Chem Catalyst Diksha. Okay, so you can go and watch that. Go and take the PDF from there, right? So all that I have written here, right, everything. So what we have done today, as you can see, okay, from the page only you will get to know which page is important from where. So we know that from electrode potential a lot of questions are asked. Then here we know that a lot of questions are asked. So from there you will get to know that, you know, everything that I have taught you, right? This is so much in detail that you don't need to do anything else. If you have done D block, DNF block from NCERT, that is more than enough, right? Okay, chalo. Now I'll be waiting for your comments in the comment section. Let's see how many of you give your amazing, beautiful comments in the comment section. And till then, bye bye, Janushika, Shavas, Darshine, and yes, okay. Okay then. Bye bye. Take care, everyone. See you all in the next class. Bye bye. Now, next I'll be starting with P block, but only if you say so, right? So I don't have any obligation to do that, but if you ask, then I will do. But for that, I don't need that much low audience here. Like, you can tell me the timing also, according to that, I'll take the class, right? Okay then, guys. Till then, bye bye. Take care. See you all in the next class. Bye bye.